this one there is all on the podium.
Hello?
So, how many of you guys here feel very prepared for the exam? How many of you feel somewhat prepared? Okay, somewhat. Who doesn't know anything about what's going on? Okay. Does anyone feel like they don't, like, genuinely don't know anything, or they're like totally lost right now with the topics we're going over?
What is going here? I'm kidding.
Okay. Because at least, you know, I can guarantee you all the stuff that, huh? Did someone say something online?
It was me saying, what is Dylan?
Oh, that was you. Oh, okay. Yeah, so the stuff that we're doing in class right now, which is like, there's some VHDL stuff that's a little bit more complex. You don't need to worry too much about that. There will be a little bit of VHDL, but I'll kind of go over that in a second. No, you're not going to have to write any VHDL from scratch. Okay. I assure you, yes.
Are we gonna have like any adders stuff, like any of the stuff we've been doing yesterday or today?
No.
Okay.
So that you don't have to worry about.
That's all you.
Okay. Any more questions before we get started? I've got some questions here, but of course, I'd love to take questions from you if you have anything that you want me to go over after. But I've got some stuff already.
We're going over the practice.
I'm going to go over some questions I just made right before this, and then also we'll do some practice exam questions. We'll probably try and do all of the practice exam questions so that you can see how to do them, okay? But I'm just going to quickly give you an overview of all the topics that we've got. So as you guys know, we're doing, you know, just the basic number systems. So that includes understanding binary, understanding hexadecimal at the very least, as well as how to convert different numbers from different bases. So for example, can you convert a number from binary to decimal? Can you convert from decimal to any other base? For example, like base 5. All right. And if you need a refresher on how to do that, I'll go over it really quickly. So our first example, and this is something that you will do on the exam, maybe not this specific base, but they're not that hard, so I wouldn't panic. So we're going to go from base 10 to base 5. Okay. And this is a question that you'll see. It's just like, you know, convert this to this. And you should be able to use any method that you understand. However, I'll give you the easiest method that I always use when I do these types of questions. And that's called successive division. All right, so what you do is you take the original number and then you divide it by the base that you're trying to target, okay? And that's 5. So in this example, we divide by 5 and we get something. So 497 divided by 5, that's 95, 90. It should be 99, okay? And then how much is the remainder? I think it's 2. So that gives us 99, remainder 2. The question in the exam probably won't be as hard, but I mean, you could do some long division here if you need to get that answer. All right, the important thing that I would do is just start circling these remainders here. And you're going to call this the least significant digit. And I'll just label it there. I know it says LSD. I'm just, okay, whatever. It's the least significant digit. And you're going to use that when you try and get your answer at the end, all right? So you take that digit here, the one that you calculated, and then you use that as your next step. So you write it down here. And of course, that comes from there. And then you do the same thing. So you divide by 5, and you get something. Yeah, so you get 19. Remainder, what's the remainder? 4. Right. So we get remainder 4, and we'll circle that again. And then we just keep going.
4 is the highest that we can go.
Yeah, so in base 5, if you remember, we can only have these values. So 1, 2, 0, 1, 2, 3, and 4. And of course, it makes sense because you've got 5 different digits that you can have. Base 10, for example, has 0 through 9. That's 10 different digits. So whatever base you're working in, that's like the maximum amount of different unique digits you can have in your number system. So if you get an answer that has a digit of like 6 or 5, when you're trying to convert into base 5, you already know that you're wrong. Okay, so that's when you can say, I need to take a step back and rework this. All right. So we do it again. And what do we get? We get 19 divided by 5, which is 3. And then that's remainder 4 because that's 15. And then we have 4 left. So let's circle that. And then we do the last one. So it's 3 divided by 5. Okay, what is 3 divided by 5? Well, we can't fit 5 into 3. So we have a final answer of 0. And this is how we know when to stop, right? So once we hit 0, we write our remainder, which is just 3 because we didn't do any division. And then here, and then we can say this is our most significant digit. And if you read it out like this, you finally get, so you get 3, 4, 4, 2, base 5. And that is our final answer for our thing in base 10. So we can write it out like this. So these numbers are equivalent in value. All right. And if you want to verify, you can always go the other way around, right? And if you get a question like this, it's the same method. So if we want to convert back from our original number, from our answer back to the original number, just to verify that we did it right, we can expand our number using the polyadic number representation that we saw in class. So we look at our digits here, and since we're working base 5, I like to just write out the powers of 5 above the number like this. So we start with 5 to the power of 0, 5 to the power 1, 2, and 3. Okay, and what do I do next? And then I sum everything, right? So we can start with the biggest digit. So the number in the 5 to the third place is 3. So we start by writing 3 times 5 to the power of 3, right? And then we add it to the next term, which is 4, which is in the 5 to the second place. So we get 4 times 5 to the second. And then we do the next digit, so we get 4 times 5 to the 1. And then lastly, we have 2 times 5 to the 0. All right, and then all you have to do is do the expansion, so multiply this all together. So we have 2 times 5 to the 0, which is just 2. We have 4 times 5, which is just 20. We have 4 times 25, which is just 100. And then we have 125, 5 cubed, times 3, which is 375. All right. And then we add that all up. That's 375 plus 100 plus 22. And that should give us the same answer that we had before. All right. Are there any questions about what we've done?
So two kind of similar questions.
Mhm.
We only do that in fully added form when we converting to base 10.
Yeah, I mean, so that's the easiest way to do it. All right, there's other methods. Like I'm sure that you may have seen my video on like using corner scheme. That's one method of doing it. This is probably the easiest way to do it. And if you want to represent any number in
Would you be able to go over the order scheme after?
I can after I go through all my
Yeah,
questions.
'cause I got confused in the first.
That's fine.
example.
Yeah, I can do an example at the end.
And there is another question.
Oh, sure,
for
sorry.
The first example you did. So when we do that, like divided by the long division.
Oh, this one? Yeah.
Kind of thing. Like when we do this, isn't it only when we have the like base 10 form, and then any other base? Or
Yeah.
you can do it for any other form. Because I remember like from the
Mhm.
from the honors game, you had to convert like when you do small to
Yep.
high to small.
Yeah, there's the two different options, right? There's the lower to bigger base, and then there's the bigger to smaller
The
base.
small to large, the large to small you convert
Mhm.
like the base you add to the other
Mhm.
base that is.
Yeah, you have to, because I mean, here it's really easy because we're working in base 10. We already fully understand how base 10 works, but once you start working in mathematics that's in a different base, for example, base 7, when any result that you get can't be over the number 6, then you have to start thinking about it differently. I'll just go over an example at the end with the Horner scheme, because if you're trying to do some other type of conversion that's not from base 10, I would recommend using the Horner scheme, because this can start to get a little bit confusing. And I'm sure it was probably confusing in the slides because you don't see why we're doing the conversions. Like with these numbers here, but yeah, let's go over it at the end. Okay. Yeah.
I do got a question.
I mean, it's possible. Like, are you asking, like, do you have to do binary subtraction in a specific method?
Yeah.
If you do have to do any binary subtraction or any operations like that, it'll be specified. I know that he went over shift and add algorithms for like addition, for example. But I don't think that stuff is going to be covered anyways, so I wouldn't worry too much. I got a message in the chat. I don't know how to read this.
I can just say it.
Oh yeah, sure.
Will calculators be allowed on the exam?
Say that again?
Will calculators be allowed on the exam?
No, there's no calculators allowed on the exam. Hopefully that doesn't scare you and makes you feel like the computations you'll be doing are not as hard. Okay.
All right.
So that's my advice. It's not going to be too stressful. All right. Or any other questions about this stuff? This is the simplest stuff. Yeah.
Is Horner scheme recommended for when we're going from a smaller to a bigger base? Is that the recommended method?
I mean, I think it's really just based on what you can do the easiest. I mean, for me, it's easiest because that's the only one I really know. The reason why I'm not really covering it is because I'm trying to give you a hint on what's on the exam. So okay. Anyways, does that help? All right. Does that help at all? I hope so. Okay. It is useful. Okay, because I mean, we can inspect the question and choose what method that we want to use for any given question, but computers typically they only follow one specific algorithm. That's the reason why we cover stuff like shift and add algorithms. Even though it doesn't really make as much sense to us, maybe it makes more sense to the computer because it has to have a one size fits all algorithm that works for everything, right? And the Horner scheme is one of those algorithms that works for any type of base conversion in a step-by-step way, right? You know, will the excitation tables be provided for the JKD and T flip-flops? Okay, so I got a lot of questions about whether we're going to provide that stuff, and I think no, unless it's a JK flip-flop. Okay, so JK is a little bit harder to remember the behavior of versus the D flip-flop and the T flip-flop. If you know what the T flip-flop does, for example, it is very, very easy to derive the excitation table. Because, for example, if you just write it out like this, and you write out the different possible combinations of transitions, you can easily figure out what happens. So if I want to go from 0 to 0 on a toggle flip-flop, what do? I'm not going to toggle the input, so I just keep it 0, right? If I want to go from 0 to 1, I'm toggling the state, so the toggle turns on. If I'm going from 1 to 0, it's toggling again, right? 1 to 1, no change, just don't toggle the flip-flop. So you will probably be expected to do something like that. Yeah.
I was gonna ask, are we like allowed to use a cheat sheet? No.
No. So again, we did it last year. But I think that we're trying to make it a little bit, I'm not going to say easier, but it is easy enough that you do not need any external resources. All right.
Does it have the same behavior of an XOR?
You're asking, well, I mean, if you look at the table, technically yes, but it's a memory component. So, I mean, the table kind of looks the same, but it does something different, right? And this is not really a truth table. This is just showing what do I need to pass into the flip-flop to start at one state and get to the next, right? So there is some differences to be understood there. And you can do this for a D flip-flop as well, very easily. There's only one input D as well. JK, if you remember what the SR latch does, you can extend that onto the JK flip-flop, because remember, J is the same thing as the set input, but K is the reset, and you can derive it from there, but we'll probably give that if necessary. All right? Yeah.
Would you say like reviewing the homework to do a study method?
Yes. That's all I can say. I mean, the homework questions were made with the intention of them being the most similar to the exam questions that you'll get. All right. And we did not grade them by accuracy, if you did not already realize that. And hopefully you didn't realize that was the whole point. We wanted you to work on them very, thoroughly and make sure that you understand those questions. Again, if you realize that and you just didn't put any effort, I would highly suggest that you go back on the website because those solutions are all there for the previous homeworks that have been released. I think at least homework 1, 2, and 3, those solutions have been released on the website. So go back on there and just make sure you understand it.
In the practice exam that you guys put in Canvas.
Yeah.
There were a few questions like that you have to write to, like for example, they ask, for example, describe what is an S or Latch. Do you think it's gonna be like, it could be like questions like that where we have to write?
Yes. Yeah. I think you'll get some questions like that. So just understand what the components do. And those, again, are subjective questions technically, but they're not hard to answer. If I ask what is a D flip-flop or a delay flip-flop, you should understand what it is. I mean, it's a memory component, and you just say that it's a memory, and it does this when I put in an input, and and inputs can only go in when there's a clock signal, like stuff like that. It's not that hard. All right, so I'm going to go over some of the more early stuff. I'm going to do an example of a half adder. So I know that he covered this in class, but I'm just going to show you from basics how to start from small truth tables, generating functions, up to more complex examples with those K-maps. And I know that a lot of you have done it, but again, this is more what we're going to be covering on the exam. So I wanted to do that. So what is a half adder? So I'm going to draw out the component here. So a half adder takes in 2 inputs, right? And it gives out a sum bit and a carry bit. All right, and let's see, half adder. And all it does is it takes those 2 inputs, A and B, adds them together. And of course, what are the possible combinations of additions you can do? Well, we can draw that out in the truth table like this. So let's draw out our truth table. So the possible combinations of inputs that we can have are 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. And anytime you write out a truth table, when you write out those different combinations of inputs, you should always have it in counting order. And if you didn't already understand what counting order was, each entry, each row should be ordered in binary from 0 to however many entries you have. So you can see this one in binary is 0. This is 1, 2, and 3. Does that make sense? So you should always have it like that, especially because the way that we're grading is we're looking at the table in counting order, and if it's not, then you'll get something wrong on the exam. Yeah.
Is there partial credit?
Yes, but I don't know exactly. I can't tell you what partial credit there will be, but we're not like just going to see that there's a small mistake and then everything is gone. If we see that you understand the question, we'll probably be giving you something, but I can't elaborate further than that. Yeah. All right. So what is the behavior of our half adder if we're just doing addition? If we have 0 plus 0, what do we get? So our sum bit is 0, and of course there's no carry, right? 1 plus 0 or 0 plus 1? Yep. And then same thing for the next one, right? And then 1 plus 1, what's our sum? Okay, the sum is 0 and the carry. And of course, if I write out those values just in decimal, you can see that this is represented as 0. If we represent this as binary digit 1 and this is binary digit 0, we have this is 1, 1. And then if we read this together, remember it's 2. And that makes sense because you're adding 1 plus 1. So that's what that carry means. All right. And if you want to derive equations for these 2 outputs so that we can figure out what goes inside our block here, well, you can very easily do what you did on lab 1 and just say, okay, I'm going to look at where those inputs are 1, and I'm going to derive those equations like that, right? And this is called the sum of products method. So we have sum of products. All right, and so how do we derive those equations? Let's look at one specific output. Well, this one's very easy. We just look at where is it true, and then we check what are the values of A and B that make the output true at that specific spot. And we can see that they're both 1, So that means that when A is true and B is true, then our output is going to be 1. And since that's the only case where the carry is ever 1, that's going to be the only term in our equation. All right, does that make sense? All right, what are they saying online? Can you read it out to me?
Instead of doing a sum of products, will it suffice to say S is XOR by inspection?
For something as simple as this, yes, but it won't be that simple, right? I'm just showing this example to explain, how to do it in case you forgot, and then we're going to build up to a harder example using K-maps, which is more likely what you'll get on the.
What I was gonna say, we'll be able to choose like which way do we get to the equation, or will you ask us like do some products, do products from?
So it'll ask you in the question, either do sum of products, product of sums, or to do both. Okay. And so if you remember homework 3, I believe it was homework 3 where it said, here's this table, do both. Are they the same? Something like that. That might be something that you would try and practice. So make sure that you understand both and don't rely on just one method. Okay. And if we wanted to do product of sums, instead of looking at where where the output is true, if we want to do this for the sum, we look at where it's false, right? So this could be useful in cases when, for example, it's always true except for one spot, right? And that would make it a lot easier to just circle, okay, well, it's just false at one spot. Let's just focus on that, okay? And so that's why you might want to use product of sums. And so if I do it that method, the way that we do it, is we look at the first example where it's false for our sum, and we see what were the two input values at that spot. Okay, A was false and B was false. So, yeah. Okay, sorry. I don't know. Someone was talking. So what do? Do we write it out like this? A is false and B is false?
No.
Why?
Your audience.
Oh, my audio's? No, that I have it streaming on my iPad. So, you have a question? Mm-hmm. Right. Right. So we're actually trying to get our function to still output 1 when it's supposed to, right? So what we're doing is we're taking those cases where it's 0 and we're trying to eliminate them. All right. Anyways, so sorry about that. When you're doing product of sums, you're always trying to just eliminate all those cases. You're just telling your function, do not turn on where I specify, right? So instead of writing down exactly what it says on the inputs, you actually invert it, right? Because we're looking at where it's not supposed to be, and then we have to say, okay, every other case, turn on, right? So we can say, all right, let's invert it. Let's take away those nots, and then we just add it together. And that's our first one. For the next one, well, see that the inputs A and B are both on. So what is it going to be? It's just going to be exactly the opposite, right? So it'll be A naught plus B naught. All right, are there any questions about what I've done so far?
We can do this by K-map, right?
Mm-hmm. Yeah, so again, this is just straight from the truth table. And then I'll get into the K-maps right after this. All right, are there any questions online? Okay, so this is a super easy example, right? You're just doing 1-bit binary addition. You're not even really building something that complex. There's only 2 inputs, but what about when you inputs? All right, give me a sec.
So you can have a half adder.
Mhm.
Or
So if you add an extra input to the half adder, what are you doing? Like, let's say that you want to use these adder components in further applications. Like, let's say you want to make a 2-bit adder without doing that gigantic truth table that you did in homework 3. Well, you would put 2 components together, right? But to do that, you need to have an adder that takes in an extra input, which is a carry in from a previous addition, right? Because that's how we do normal addition in decimal. Binary is no different. So we want to actually build that right now. So we want to expand what we've learned and build a full adder. Okay? And a full adder, very, very similar, takes in two inputs, but then you have this extra one, which is called carry in. And this is going to be the carry from a previous addition. All right. And then same exact thing. We have carry out and the sum. All right. So again, now there's three inputs. It's become slightly more complex, but we can approach this in the exact same way. So let's write out all of the possible input combinations into our component here. So we have A, B, I'll put C in right here. And then we'll do C out, carry out, and then our sum bit. So possible combinations. How many possible combinations of inputs do we have based on this? 8, right? So we have 2 to the power of the amount of inputs we have. So that means there's going to be 8 entries. If you do not have the right amount of entries in your truth table, you will not do well on the question. Okay, you need to cover every possible input combination in your table. So let's go in counting order again. Let's go from 0 to 7 because those are 8 values. So in binary 0, 0, 0, 2, 3, 4, 5, 6, and then 7. And I remember when I was first learning this stuff, I kept forgetting the order, but you know, eventually you start to get used to writing in binary. You start thinking in binary, you forget what decimal is. It'll happen eventually. Okay. So don't worry too much. Anyways, so what do we have to do here? Exact same thing. Let's do those additions. All right. So in our first case, we get 0 plus 0 plus 0. And then we have 0 plus 1. And then I'll fill out the rest. So 1 plus 1 is 2. Right? And then if we add 1 plus 1 plus 1, what do we get in binary? 1, 1. So what are my outputs here?
1, 1.
All right. Okay, so that's the only time that you could ever get the value 3 is when you add all 3 things together. So our table has gotten a little bit bigger. Does anyone actually want to do product of sums on all of this stuff right now? On both of those functions?
No, but can you repeat what is the logic of C in?
C in is basically just another digit. Like you remember when you do addition like this, you have 5 plus 7, 15 plus 7. How do you do this? You do you'd have to basically take the value that you get, which is what? What's 5 plus 7? Yeah. And then you carry. All right. Well, how much do you carry? 2? 1? Yeah. Yeah. So it's basically taking the value from that previous addition that you did and using it for the next addition, right? And that's how you'll implement binary addition in
That's not the C out.
you asked for the carry in.
So what is the difference between C in and C out?
There is no difference, but basically it's saying for this specific addition operation, I need to pull in this value. And then based on that addition, did I overflow the amount that I can hold? Like, can I do in decimal, can I do 5 plus 7 and store it in a single digit? No. So then you have a carry out value. Do you understand? And then in the next operation, when you do this operation, you have a carry in value from that previous addition that you just did, right?
Basically, that one on top is to carry out from the 5 cent. Oh, it's carry in the 1.
Yeah. And so it becomes relevant once you start doing multiple digit, binary addition. Like let's say you want to add 8 bits together. It's a lot easier to just put these components together and say, okay, add the first two digits and then go do the next one and then et cetera, et cetera. All right. But you need to know the result of the previous one to know, do I need to add an extra number? Like, because did my previous one overflow or not? Right.
What do you do with like the last pattern has like a carry out? You just add it to it.
Well, it just becomes the most significant bit, right? Just like when you do normal, when you do normal addition, like 15 plus 4, what do you get? You get 9. Okay, technically this isn't a carry out, but there's just a value hanging on its edge. You just bring it down, right? And if you have a carry on the very end, you just bring it down, just like you would in normal decimal addition, right? All right. So do you really want to generate all these equations? I mean, we can, right? So let's do that really quickly. So let's do the sum of products for this one. And we get, so C out equals, so the first one, carry in is false. So and then we have Cn is true, B is false, or no, A is false, sorry. And then Cn is true, A is true, B is false, and then finally they're all true, right? So obviously this is not the most simple equation that you can get. There's a lot of simplification that you can do, right? You can go through with those binary or Boolean algebra laws to simplify this. Like for example, we could take these two terms here. If I put them right next to each other, you can take out the AB, right? So you get AB and then Cn not or Cn. And what is that? What does this evaluate to? Yeah, so it's just going to evaluate to 1. So eventually we can simplify these two terms into just AB, right? And you can go through that whole process yourself. Any question that you get on the exam won't be too complicated, but I would expect you guys to know that without having those sheets. But again, the stuff that you're going to be tested on is not going to be super complex. It'll be pretty easy to understand. A lot of these rules are just based on normal mathematics that you already know.
What about the consensus law?
Yeah, there's no consensus theorem question on the exam. I can promise you that. All right. I mean, there isn't really much point of testing that because that you just plug in and see what happens, right? So don't worry about that.
So one small thing.
Mhm.
We are like this. We can actually solve it by using k-maps, right? So
Yeah, so
are we supposed to go the Boolean algebra, or we can choose?
yeah, so if the question explicitly says use a sum of, just use the sum of products from the truth table, then you're not going to use the k-map to do any simplification. Basically, if it says use Boolean algebra laws to simplify, do not use a k-map. You get what I'm saying? So, but of course, there will be questions where you need to do those k-maps.
Will you specify if we need like this? Like if you say minimum sum of products, then like we have to simplify it.
Mm-hmm. Yeah, if it's specified, which it should be. But of course, if we don't want to do this and we're really lazy, we don't want to do any of these Boolean algebra laws, let's just turn it into a k-map, right? So let's go ahead and turn this into a k-map. You guys all know how to turn this stuff into a k-map? Okay.
Is there a reason why we don't we don't look for the S in?
Oh no, you can. I just don't want to do it right now. I just want to show you one example. You'll have to do this for every single output that you have, right? So, oh yeah, hold on. I flipped it. My bad. Yeah. I guess I probably should have. I guess because of the way that I have it oriented, I'll just flip it horizontally, and that's fine too. So it doesn't really matter which way you do it as long as you're consistent with your choices, right? Okay, 1, 2, 3. All right. So the way that we label our k-map, you guys all remember this? For the left side is pretty easy because we just do different possible combinations of Cn, which are just 0 and 1. All right, and then we have to do the different combinations of A and B. All right, and so the way that we do this is we say, okay, first case, A is 0, B is 0. Second case, A is 0, B is 1. And you'll see it's going from 0 to 1 in binary. And then I'm sure that you've all seen, as in homework 3, we don't go from 1 to 2. We go from 1 to 3. And I'll explain why in a second. All right, and then we go to 2. So I'll just write out those digits. All right. So that's the order that you'll create your k-map in. And this will make it as easy as possible for you to solve. And the reason why is because what are we actually doing in our k-map? We are looking for adjacent, we're looking for the places where the truth values are next to each other. And when we circle those things, when we circle our groupings, we're looking and seeing what values on the top, what value does not change, all right? Because that's going to be the only value that determines what that truth value is in that group. And here we can see from adjacent digits here, what changes? Well, this digit changes from 0 to 1, but it's just one change. From here to here, all we see is that this digit changes, so it's just one change again. And from here to here, we can see that this last digit changes, but again, there's just one change in between each consecutive value. If we wrote it out with 2 here and 3 here, you'd see that there'd be actually 2 changes between this. Because if we go from 0 to 1 to 1 to 0, what's changing here? Like both of the bits are flipping, right? So it'll make it a little bit harder. All right, so that's the reasoning why you want to label your K-map like this. And this code is called the gray code, which I'm sure that you'll see later on in a different class, but it's basically just saying, I only want 1 bit to change in each number in my sequence, okay? So we fill it out by looking at our truth table. This specific little cube here represents 0, 0, 0, so we can map that out and we say, okay, well, that value there is 0. All right, and then we can keep going. So this one here is 0, 0, 1, so it's that one. So this is also 0. And then here, be careful, because this is the most common mistake I see. This is 0, 1, 1, right? Because we're not doing it in order. So we look here, 0, 1, 1, and we have a truth value of 1. And then we go back to 0, 1, 0, which is a 0 again. Does that make sense? And then let's fill out the rest of it. So there we go. All you have to do now is do those groupings. So in this example, the groupings aren't super great from what I can see. We've got 4 ones here, but they're not ordered pretty well. So we'll just have to circle them like this. And then another group like this. And another group like this. All right, and so you see that there is some overlap. But the most important thing in a K-map is that you need to ensure that every single value is circled, every single truth value that you're looking for. So if you're doing a standard sum of products, you need to make sure that every one is covered. And if you remember from the homework, if you're doing a product of sums, you need to make sure that every 0 is covered, or else your function will not operate as expected. So I'll go ahead and get these terms out. So the way that we figure out what term is being circled by this orange one is we look at the 2 sides that are, we look at the column and the row that this thing is covering. So we see on this side, Cn is always 1 in every single box that's circled by this orange grouping, right? So we're going to say it is essential that, like, the Cn term is essential in determining what our value is, because it's always 1 in this case. So we say Cn is part of it. Then we go ahead and look at the top. All right, so what do we see? What never changes between this square and this square? Well, we look at this and we see
B.
Yeah, so we see that B here is 1 in both of those cases. So we know that B is essential in determining the value, the truth value there. All right, and that's it. And then we can do this for the rest of them. So for this one, we have, if we look at the Cn column, we see that in each of those boxes, it changes. So we know that Cn does not determine it, right? But we see that on the top, A and B are always the same. And that gives us our term that we want. And then lastly here, we can see that Cn is always true in that little green circling. And then on the top, the only thing that stays the same is what? In the green circle. It's A, right? So that's what we do. And then product of sums, all we do, combine all of them. Great, right? Yeah.
Should we say the
For which one?
of the read each?
Well, so if you look here in the green one, we're looking for what changes or what does not change. And we see that A stays 1 in both of these examples, right? So that's why we include A, positive A, inside of our term. B goes from 1 to 0 between this one and that one. So we say, okay, B is not essential in determining the value there. Yeah.
So you don't write B
No.
No.
So that this is the whole point of the K-map. It's to see what terms, what inputs are essential in making these values true, right? And doing it this way, what do you see? You get a term here that has 2 literals. This one has 2 literals, and this one has 2 literals. But what do you see from the original function that we derived like this? I mean, it's way bigger, right? And of course, you can go ahead and simplify it using those manual methods, but why would we want to do that? When those K-maps just say, okay, let's inspect it in a different way and just eliminate those terms that we know for a fact do not determine the truth value, right? And that's how we get this very, very small function that describes the same thing. And you can actually use the K-map to determine whether your simplification using those Boolean algebra laws is the most simple most of the time. Right? I'm sure that you saw in homework 3, sometimes there are not unique groupings. In this case, there are no other groupings I could do. I mean, I have to do an overlap on this term because the smallest group that we can do is, well, I guess we could circle them all as 1s, right? But that's not the biggest grouping possible that we could do. You have to do the groups in groups of 1, 2, 4, 8, etc. It has to be a power of 2. You can't group it another way. And the reason why we do this is because we're working in binary, so we work in powers of 2. Are there any other questions about this? So then that's your equation for C out here. And you can go ahead and do the same thing for the sum later on. All right. But this is just generally the approach to, first of all, building the K-map from the truth table and then solving those equations. You have a question?
So when they overlap,
Mhm.
it's like just 2.
Mhm. Right.
If they can only overlap like on one side, right?
I mean, it doesn't really matter if you had an example like this. Okay, let's say that your table looked like this, right? So you have this very simple one. Well, here you just look for the biggest possible group. Okay, always start at the biggest possible group because I could circle them like this. Okay, is this going to give me the most efficient thing if I inspect it? Of course not. I could also circle it like this too. They're all possible, right? But we always go for the straight up the biggest group here. There is some overlap that's inevitable, okay? If you always fill out the biggest group, you might get some overlap. That's not the really important part. It's just the important part is that you have biggest possible groups chosen. It only becomes an issue once you have these values called, the don't care values, which could be in our K-map, where you could get these really like non-unique circling in groups and stuff. And we can see that in this next example I'll go over. So, all right. So I'm going to go over a K-map example with those don't cares. So I know that you guys like that, but it actually is kind of easy once you get to understand it. So let's do that. How are you doing, Omar? How's it going? With your Arizona tea.
Of course, that's why I'm glad I had to make a pit stop.
You able to get a parking spot?
Mm-hmm. The lot by Nala literally has like infinity parking spaces. Like there are a lot of them right now.
Yeah.
I don't know what Jason was talking about.
I don't know. I got my staff parking.
Unfair about it.
All right, no scrolling allowed in my. I'm not joking. It's fine. All right, so have all of you seen a K-map that looks like this? I pray that you have, because if not, then you definitely dropped lab 3 and 4, which is not great. But okay, so what is the don't care value? Can anyone explain that to me? Yes.
Is a value that could be a 0 or a 1, and it wouldn't affect our function, and therefore we do not care about its value.
Right. Did everyone get that? Okay. So it doesn't matter because this is usually in circuits when we have possible outputs, but we just don't need them. We don't use them at all. All right. So yeah.
Isn't it also like, since you're like going to the states and you're not expected to go to that certain state for it?
Well, this isn't even just states. I mean, this could be even in basic circuits that don't use any like state machines or anything. They could have don't care values too. Like let's say that you wanted a 7-segment display to go all the way up to. Let's say that you made a 7-segment display like in lab 2 that goes from 0 to F, right? That's what you did. But what if I didn't go all the way up to F, but I still had 4 inputs? I could go higher, but everything after that, I don't care about its value. Like if I set the inputs to 12, but I'd never made any logic to make the LED turn to 12, then we don't care about those values, right? It basically just don't do anything in that case, or do something, but we have no definition for it, right?
Okay.
So that's an example of like just straight up combinational logic where you'll have don't care. So how can I group these using sum of products? Well, let's try and build the biggest possible groups using the ones and the don't cares. All right. So let's do that. So I see a grouping here. This one here. All right. So I've grouped a 1 and an X together because, again, you can use it for whatever you want. We're going to say that this is our first group. And then we can do another group here. So, again, another 1 and an X. These are the biggest possible groups I can find. And then we could circle this one and this one. So, again, when you have those digits that are opposite of each other like that, they are still considered adjacent. All right. And that's something that you really need to be careful about because sometimes you won't see that, maybe in a bigger K map, there's 4 of them in the corners, which are also considered adjacent, right? But you need to be paying attention. And also stuff that is just right opposite each other like this, maybe you don't realize and you circle it, just like this, but then you have a less than optimal solution for your function. Yeah.
Does the number of groups matter, or is it just the size of the group? Yeah, all the ones with just 2 groups, if you don't include the 1.
Yeah, so you could, but if you remember, the bigger the group is, the more terms you eliminate from the equation. Okay, and I don't know exactly a great way to show that, but
I'm saying that you can do it in 2 groups if you circle the 1 and then you have the same green grouping that goes through.
Oh, yes.
So yes, the less terms you have, it's a more optimal solution. In some cases, there can be multiple optimal solutions, but we won't give you those, so it's easier for grading. But yeah, the number of terms does matter, and the size of the terms also does matter.
Yeah, so you're saying that we could do it like this?
Yeah.
Yeah, so I mean, I think that that's also fine. I don't think it actually makes the solution any smaller in this case. The question that you get probably will not be like that, as you mentioned. So, but anyways, if I use those old groupings I had, we can literally just get the terms exactly the same way. Just pretend that those things are ones again, and just look at the side, see what changes, look at the top, see what changes, and generate your function. All right.
Can I make one random note?
Yeah.
This is something that I thought of the other day. If you ever had trouble with consensus theorem, if you couldn't remember that, this is kind of like a visual representation of it. You can see how this, like, where's the laser pointer? This one. You can see how like this red group and this yellow group cover those 4 terms, and circling this group would be redundant because all 4 terms are already covered. That's consensus theorem right there. So, if you have like an equation and you think that there's consensus theorem, but you don't remember it actually, you can make a K-map of it, and that might help a little bit.
Yeah, because again, I'm not going to circle this, even though I could. All right. As I said, you can always make more circles if you want, but try and get the least amount of, try and approach like the least amount of groupings and the biggest ones. But again, there's a lot of cases where there's not non-unique solutions, which is exactly what you saw in homework 3, where it was like, oh, do the K-map and tell me, are the solutions unique, right? And you can figure that out. If you see those different possible things that you can circle that still give you, a small solution, then it's probably not unique, right? Are there any other questions about this? Yeah.
Are we going to be testing Quine multiplicity algorithm?
No.
No.
I promise you won't, but I promise you Quine McCluskey will not be covered. However, it's still something that's important to understand as just a concept. What is that? What? Oh, okay. Yeah, I mean, look, it's still good to understand that Quine McCluskey is an algorithmic way of solving these things. I don't know if any of you guys saw my 6 variable K-map that I sent in the Slack channel, but I don't know if you would want to be doing something like that once you have more variables, right? Let's say you have 100 variables. Do you think that a 100 variable K-map is feasible at all?
Yeah.
Do you want to do that by hand?
100%.
Okay, so
100K.
for 100K, yeah, sure, I would do it too. But it might take me my whole lifetime, right? So Quine-McCluskey just describes an algorithm that you can use to take these very, very high variable inputs with these gigantic truth tables and simplify them down. How fast it is, I'm not totally sure, but it's something that you could actually code up yourself. And that's what a lot of synthesis tools like Quartus most likely use as their main algorithm to simplify down your functions.
The other note with Quine and McCluskey compared to K-maps as well is that whether you get the optimal solutions or not in K-maps is determined on how well you can group this. So let's say that you're just bad at geometry, you can't always find the optimal grouping, then K-maps are just never going to give you the optimal grouping. However, Quine-McCluskey, if you do it correctly, is guaranteed to give you the most optimal solution every time.
Yeah. It's definitely a very valuable thing to understand. So I would say know what it is, but we will not ask you to perform the algorithm in any way.
We will not.
All right. So I'm going to go over same thing, bigger example. So
Or the biggest that we're going to test it on?
no, I'm definitely going to give you a 6 variable K-map. No. 4 is the biggest that you'll. 4 is the biggest reasonable size K-map that you should be able to do. Okay.
5 is technically possible, but it's basically like 4 2-variable K-maps stacked on top of each other. So you have to see like, oh, these two terms are on top of each other, so I can circle that. And that's kind of annoying to do and not worth it. So 4 is the biggest K-map that will be.
Yeah. So, okay. So something that you should know, again, is these 4 variable K-maps. I would just make your own K-maps and try and solve them, try and generate equations for them. And again, one K-map usually represents a single output of your circuit, all right? So in this case, I want to get the logic function from my for my circuit, but I don't know which method to choose. We will, if anything, we will probably ask you to do both. So just make sure to know both ways, okay? But in this case, I'll probably choose product of sums. Why do you think that? Why would I choose product of sums here?
There's less zero.
Yeah, so there's a lot less zeros than there are ones. And honestly, I think it's good to just do both. Because again, you might stick to one method, but there are cases where it's going to be much faster to just go with the other, even if you feel a lot less comfortable. I always just jump straight to sum of products, but product of sums is useful in these cases. So here, I'm going to show you some magic with these groupings because you can group all this stuff in 2 groups, all the zeros. How can I do that? All the zeros in 2 groups.
You do one like this.
Which one? Like in
wait.
tell me the boxes.
I
Yeah.
already saw them. The 2 on top, the 2 on the bottom,
Okay.
to the left. Then just the 2, the ones in the middle within the or
okay.
like
All right. Okay. No, that's perfect. All right. So be careful when you're working with these things. There are adjacent groups, there are adjacent terms that you just might not see, right? And it's really perfect because we've got all of these don't care values, which make it super easy to make 2 big groups that simplify our terms down very highly. If we look at, if we actually solve this and the same method that we already just did, we would get 2 terms. Well, 2 products, which would be this. So we've taken this big K-map, and now without doing any Boolean algebra, we can just straight up say, okay, here's our simplified term.
But Mr. Newman, A is 0 in that column, so why is it not negated?
I already explained that before you got here. I'm not talking about that again. But do you guys understand that part? Why did I invert it in product of sums? Yeah. Okay. Are there any questions? I'm not going to do it every single time, but this is what you need to know how to do. Yeah.
So for the don't care values.
No, you don't. I mean, you could group it like this. It's a group of 2, but is there a bigger group that you could make? Certainly here. And if you try and if you do this green circle, what term are you going to get? You're going to get a bigger term, right? So is it simpler to make that bigger group with those don't cares? It actually is, because you see it becomes smaller, right?
And just to note on an exam, if we tell you that you can circle don't cares and there's an optimal solution like that and you choose the smaller one, that will be points off because we're looking for the most optimal solution.
Yeah.
If you don't realize like that there are bigger groups to make, you just simplify the equation Boolean algebra.
Well, you're not supposed to. The whole point
No.
is that we want you to get the simplest thing upon inspection as quick as possible, right? The whole point is to avoid that.
If you do Boolean algebra after you derive the equation from your K-map, we're gonna probably ignore it.
Yeah. I did see that a lot in my section. I saw it a lot, where you did the K-map and then you did more logic simplification. But it's like, what's the point? You just did the K-map for that, right? You're supposed to use the K-map to do that. All right. Are there any more questions about K-maps in general? Don't cares? You have a question? No? Okay. Does everyone feel comfortable with K-maps yet? Right. Show of hands. Who feels comfortable with this? If you got a question like this, would you be able to do product of sums and sum of products? I hope so. Okay. So that's basically all the logic portion. All right. Then there's the harder stuff. So this is the easy stuff, but this is the harder stuff that's coming up. So anyone, we want to do the practice exam? What are you guys feeling? Or does anyone have any questions? Yeah. Number 4 on the practice exam.
Actually, 5 may be quicker.
4 is the one I least wanted to do. I can't confirm or deny if Omar wants to do number 4, design 8x1 multiplexer with 4-to-1 and 2-to-1 multiplexers. He can do it. You want to do it,
You
Omar?
guys want me to do that?
Yes.
All right. Pull up question 4.
All right. So question 4 on the practice exam. Here's what we ask you. We ask you derive equation for a 2x1 mux. Then we ask you to create a 4x1 mux. And then we tell you to create an 8x1 mux. And then just give me 1 second to get. All right, so can anybody tell me what a multiplexer does? Raise a hands or shout it out. Yes.
Chooses a specific signal out of various.
It chooses between 2 values. Good. So for a 2x1, or it chooses between 2 values for a 2x1 mux. So we're going to start with our truth table. We have 2 inputs, A and B. Those are our inputs that we can select between. We have 1 select line S, and then we'll have an output. I'll just call it Y. You can generally name these whatever you want. Sometimes you'll see X1, X0 for the, how do I erase? Oh, yeah, that makes sense. Yeah, you can generally choose whatever names you want as long as they make sense. We're going to have it so when S is 0, A is selected, and when S is 1, B is selected. So we can make this truth table 2 ways. We can either do the whole thing or we can do it with don't cares. I'm going to do the whole thing first, and then I'll show how it can be quicker with don't cares. So first, we'll just do all of our inputs. So that's 1, 2, 3, 4, 5, 6, 7, 8. Oh, I messed that up. Wait. Oopsies. Yeah. 1.
So you'll start thinking 2, 0, 1, 1. Yeah, there actually is a pattern to it. If you don't remember it, just inspect it.
All right. So for this first row, we can see that S is equal to 0. So we're going to choose whatever A is. So what should the output be? 0. All right. Next line, we're choosing whatever B is. What's the output? 0 again. Now we're choosing whatever A is. What's the output? Now we're choosing what B is. What is it? 1. Exactly. And then we'll just do this for the rest as well. That's going to be 1, 0, and then 1, 1. So now that we have this. Yeah, so remember, we're choosing the value of A whenever S is equal to 0, and we're choosing the value of B whenever S is equal to 1. So in this row right here, we can see that A is equal to 0 and S is equal to 0. So our output is going to be the same as A. And for this row, for example, B is 1 and S is equal to 1. So the output is just going to be B. Make sense? Any questions? All right, so if we were to do this using don't cares, the truth table would be a lot smaller. So let's say that A is 0 and S is 0. Doesn't matter what B is. No. So we can just put an X there because Y is always going to be 0. Let's say that A is 1. Doesn't matter what X is. Or let's say A is 1 and S is 0. Doesn't matter what B is. No, because the output is still just going to be 1. And then we can repeat the same logic for B as well when S is equal to 1. Does this make sense? How we can use don't cares for this truth table? All right, so now we can build our K-map. So I'll have A, B on this side, and then S on this side. Whatever, 0, 0, 0, 1, 1, 1, 1, 0. And then at the top, we have our 0, 1. So looking here, we'll see that it goes 0, 0, 0, and then 1. And then on the other side, it goes 1, 0, 1, 1. So then now we can make our groupings. The most optimal groupings are going to be here and here, and then deriving those out. No, I did something slightly wrong. Wait a minute. Yeah, this is why you look at your notes, guys. Yeah, what did I do wrong? Yeah, I don't think I messed the truth table up, but I did something slightly wrong in the K-map. I'm a bit rusty with the two in mux. It's been a hot minute. That should be 0. Then that should also be 0. That one down there, that should be a 0. Then that should be a 1. Then that should be a 1. That should be a 0.
The last one is a 1 because A is 1. You don't care about when X is 0, you don't care what B is.
Right here? Or
Like the last page.
right here? Oh, that is true. Yes. Thank you very much. I was looking at I was doing the K-map wrong because I was looking at this if it was in the same order. I was messing that up. Whoopsies. All right, so now we can group this. Yes.
0, 0, 1.
Oh my god. Yeah, hang on 1 second. I did the K-map in the entirely wrong order. Okay, so it's like 0, 0, 0, that's a 0, 0, 1, 0, that's a 0, 1, 1, 0, that's a 1, 1, 1. Yep. Then 0, 0, 1, that's a 0, 0, 1, 0, that's a 0, 0, 1, 1. What am I doing?
0, 1, 1.
Yeah, 0, 0, 1, 1. What the hell? Oh my god, I do need a cheat sheet here. Hang on. Yeah, the K-map should be like this. The K-map should be like this. Ignore that momentary. I set up the K-map in the truth table differently, and it was throwing me off.
That's also wrong.
This is what?
Yeah, B like the column in S is.
Do I have it reversed on my sheet?
It is reversed. If you just flip those two columns and use the K-map, it's correct.
Yeah, I'll believe you. Oh my lord. Yeah, I had it completely backwards. That is my bad. But when I missed the intro, guys. I don't know what digital logic is. But when we have this, we'll see that S is equal to, we ignore A here, and B is equal to 1. So this is going to be B and S. And then or S is equal to 0, B changes, and A is equal to 1. So this is going to be S naught and A. And that should be Y there. Should be Y. So this is the equation for a 2 in mux. And the component for it looks like this. All right, besides those K-map issues, this is what it looks like. All right, now, how do I make this bigger? It took up so much space, yeah.
the table
Oh, wow.
in the beginning, it's okay?
This one
The one that you do with the don't care.
with the don't cares, this is also good. Yes.
Because when. Oh, okay, when there's a zero, yeah.
Yeah. I was messing up the K maps. All right, so now we want to create a 4x1 mux. So how can we do that? Well, basically, we can think of a 4x1 mux as doing two stages of selection, right? It has an S1 and an S0, and it has four inputs, A, B, C, D. So this is S equals 0, 0, S equals 0, 1, S equals 1, 0, and S equals 1, 1. So what can we see in common between the selections of A and B and C and D? Well, we can see that for both A and B, S1 is equal to 0, and that for C and D, S1 is equal to 1, right? This means that first we're choosing between two values. So we can create our thing right here. We'll have A there, we'll have B there. Then on another mux, we'll have C and we'll have D. And into both of those are S1, and then out comes the output. So let's say that S1 is 1, right? Now we're choosing between B and D, where S is equal to 0, 1, and S is equal to 1. This one? No. Both of these should be S1 because first we're selecting between the ones based on the most significant bit, then we select based off the least significant bit, or you can do it the other way around. Yes. Yes. So you can see here, what's the difference between, it's if S1 is equal to 1, then it's selecting between, that should be S0 actually. Yeah, so if S0 is equal to 1, then it's selecting between B and D. So what's the difference between B and D? S1, we can see one of them has 0 and one of them has 1. So then for our second round of selection, we choose that, and then we have our same output again. Do we have any questions on this? If we want to reverse the order in which we select it, instead we would choose between A and C because they have different S1s but the same S0. And then we choose between B and D at the bottom. And then we choose based on S0. Both of these solutions are valid. So now we want to create an 8x1 mux. So when we think about it, we could use two layers of 2x1 muxes because 2 times 2 equals 8. So if we select two values, 2 times 2 equals 4. So if we, oh my God, I'm off my game. So we have 2 times 2 is equal to 4, which means that when we select two values at every time, we're selecting between a total of 4 values. So for an 8x1, since we can take advantage of our 4x1 multiplexer, we can use two 4x1 multiplexers to select between the first 4 values, and then a 2x1 multiplexer to select between the last one. So we have A, B, C, D, E, F, and G. So A, B, C, D. And then we choose between S0 and S1. And then we have E, F, G, H. This one is also between S1 and S0. So let's say that S1 and S0 is equal to 0, 1. So we're choosing between B and F. B gets chosen when S is going to be equal to 0, 0, 1. And F gets chosen when S is equal to 1, 0, 1. So we can see here the difference between these is in the most significant bit S2. So we have one final 2-to-1 multiplexer to select between those two values, and that's how you would make an 8-to-1 multiplexer. Do we have any questions about this?
What do you need to select lines?
Because these are 4x1 multiplexers. So they need an S1 input and an S0 input. Okay, yes. Mm-hmm. Like between these two solutions? No, it does not matter which one you do. They give the same functionality. Yes. Mm-hmm.
So you said that when S is 0, 0, 1 produce B, right?
Mm-hmm.
So how do you use 3 bits if we have just F1 and 0?
Oh, because for an 8-in multiplexer, because we have 8 different values to choose from, we need 3 bits of selection. So there's S2, S1, and S0 for an 8-in multiplexer. All right, does that make sense? All right, now I'm going to throw you guys a trick question. How would you make a 3-to-1 multiplexer? Do we have any ideas, right? So let's say that we have 3 values, A, B, and C. A should be chosen when S1 and S0 are equal to 0, 0. B should be chosen when S1 and S0 are equal to 1, 0. And C should be chosen when S1 and S0 are equal to, that should be 0, 1.
When you say D,
0, 1, and then 1, 0.
when you say like D never gets chosen.
D never gets chosen because there is no D. We're building a 3-to-1 multiplexer.
Values like, what are the other values? One is I just don't care.
1, 1 is a don't care, yeah.
Can we use a 4x1?
No 4-to-1 multiplexer. We're building it out of 2-to-1 multiplexers. Yes.
2x1 multiplexers and then attach the output from the first multiplexer to the second one.
And then what should be the other input of the second one?
The C.
Exactly. So if you want to design a 3x1 multiplexer, you first choose between A and B using S0 here. Then you get a second multiplexer with C as the input and choose between S1. And this satisfies the condition we've been given, right? So you can build muxes for whatever number you want by taking advantage of something like this. Does this make sense?
1,000 to 1 mux, can you do it?
10,000 to 1 mux. We might ask you that, so beware. All right. Are there any other questions from the practice exam that you want either me or Newman to go over? Yes. 5. All right. Explain the behavior of an encoder. What are its inputs and outputs? And explain the behavior of a decoder. What are its inputs and outputs? So let me just write this down. 5A is an encoder, and 5B is a decoder.
Yeah, I'll send it.
All right, so we have a dilemma. All right, that band from lab 2, they're back and they need your help again. They have 4 different speakers, okay, that they can flip on at a switch. And they want to figure out which speaker is on, or maybe which instrument is playing, in a more compact way, right? They don't want 4 LED lights to tell them which one of their 4 instruments are on. They only want 2. So let's think about this. Well, we can use binary, of course. If we assign each of these different wires a number, let's say that this is wire 0, and when it's on, it's 0, 0. Then the next one, 0, 1, 1, 0, and 1, 1. And that's all an encoder is, right? It takes some number of inputs, right? It takes a total of 2 to the n inputs, and then it has n outputs. So we can see here, because it has 4 inputs, it's going to have 2 outputs, right? And it basically just converts whichever wire is on into the binary representation of it, right? So let's say that this wire is on right now. Let's say that this wire is on right now. Both of these wires are going to be on because it's 1, 1. Let's say that this wire is on. This wire is going to be off, and then this one is going to be on because it's spitting out 0, 1. Does that make sense? Okay, do we have any questions about encoders? Yes. Okay. Did you have a question about encoder? What's up? What do you mean? Okay. No, I understand. Yeah. Okay. Let's look at a simpler example, right? Let's say you have 2 wires, right? And you know that only one wire is going to be a 1 at a time, right? Instead of looking at both wires and seeing when one is 1 or the other is 0, you can just have one wire that's either 0 or 1, depending on which wire is on, right? Let's say that if this wire is a 1, this wire right here is going to spit out 0. If this wire is a 1, then this wire is going to spit out a 1 as well, right? So by looking at this one wire, you can know what these 2 wires are doing. Does that make sense? Because the wire can be either on or off to tell you which wire is on.
same idea as a bus?
As a bus?
Yeah.
No. A bus is when you have multiple bits on one wire. But what we're doing here is it's kind of like almost trying to think of it, right? Like let's say you have a switch and it can be either a 0 or a 1, right? When the switch is 0, you can turn one wire on, and when it's a 1, you can turn a different wire on, right? This is kind of the reverse of that, right? If the first wire is a 0, or if the first wire is a 1, then our encoder is going to output a 0. If our first wire is, or if our second wire is a 1, then our encoder is going to output a 1, right? It encodes these binary wires into a binary number. So instead of looking at 4 wires in this case, you only have to look at 2. And then that tells you which wire is on. Does that make more sense?
What if you had like 1,000 different devices in a computer and you were trying to check when one of them turns on? You don't want to, and you try and store that and say, oh, which one in that list is on now? Okay, and if you were to just store, that many wires, it would be a lot harder than just saying, okay, let's compress that number down into a binary number and say, okay, I read that the 1001 is active right now. What I'm going to spit out is its binary representation, which is going to be a lot smaller, right? It would represent 1,000 binary. You can store it in only a few bits. So that's another example. It'll become more clear once we start to do some of the computer architecture stuff.
Yes.
Why it's useful, because it'll be useful in, I guess, simplifying and making things smaller when you have a lot of different inputs, and then you encode it into that.
Yeah, the decoder might make a little bit more sense, and then you can kind of think of that as the inverse of the encoder. So let's talk about a decoder, right? What a decoder does is it's just the opposite of an encoder. It's going to take in n inputs, and then it's going to have 2 to the n outputs. And then depending on the value of these inputs, I'll call them x1 and x0, it's going to turn one of these, y0, y1, y2, y3, it's going to turn one of these on, right? If x1 and x0 is equal to 0, 0, then y0 is going to be 1. If x1 and x0 are 0, 1, then y1 is going to be 1, and all the others are going to just be 0, right? If only one output of a decoder can be on at a time. So if x1 and x0 are equal to 1, 0, then y2 is going to be 1. And if x1 and x0 are equal to 1, 1, then y3 is going to be 1, right? Like, let's say that band from earlier, they have 4 different speakers that can turn on and off, and they want to control which speaker is on. But they don't want to have 4 different switches. They only want to have 2. So if both switches are 0, so binary 0, 0, then the first speaker is going to go on. If it's 0, 1, they're going to turn the second speaker on. If it's 1, 0, they're going to turn the third speaker on. And if it's 1, 1, they're going to turn the fourth speaker on. Does that make sense?
It's a form of compressing. So if we had 4 different computers that I wanted to control, I don't want to have 4 different buttons to turn them all on. I just want 2. And especially this gets a lot big. Once you have a lot more things, binary can represent gigantic numbers and a lot smaller representation. So it's going to be a lot better to have it like this.
Basically, what we do is that we switches and pairs together in a logic thing where both one depends to the other, right?
Yeah, the output is looking at it, and it's basically looking at it as a binary value, as like a combined thing, right?
Yeah. I mean, when we only have 2 and 4, it's not very apparent. But let's say you had a decoder with 32 inputs, right? You would have roughly 4 billion outputs. So with just 32 inputs, you can control 4 billion. I don't know what that was.
I think someone unmuted themselves.
Yeah, that's fire. You can control 4 billion different things if you have 32. Does this make sense why a decoder and encoder are useful?
2 to the power of 32, that's how many outputs you've got. If you have 32, literally 32 switches, you could literally control billions of devices just using this one.
Yeah, the main thing that you need to know about the encoder and decoder are these relations right here. An encoder is going to have 2 to the n inputs, and it's going to have n outputs, and a decoder is going to be the opposite. It's going to have n inputs and 2 to the n outputs.
Let me see if I understand. We have three switches. We can control 8
Exactly, yes. And if we're monitoring 8 different things, we only need 3 LEDs. Does that make sense?
Okay, so this idea is for this, like 32 switches to 4 billion is the idea of the encoder.
No, that's the decoder. So the decoder is the one where we have inputs and that gives us a lot of outputs. The encoder is the one where we have a lot of inputs and that goes to a small amount of outputs.
If you think about the name, when it says encode, it's meaning encode into binary. And binary is going to be a lot smaller, right? Decoding is decode from binary, which will become a lot bigger. Right?
Yes. Does that make sense? All right. Do we have any other questions from the practice exam that we want to cover?
Some question about like multiplication.
Sure.
Yeah. Okay. We can always do that counter question at the end too, eventually, if you want. But do you guys remember multiplication, binary multiplication? I think it was on homework 2. Okay. I'll write up some arbitrary example. Let's do some. Yeah. Okay. No. Okay. You don't have to do that. Like that's something that will become more important as we get into these harder labs because signed multiplication obviously is something that you want, right? In a computer, you never want to just do unsigned multiplication. But for now, we're not going to test on that. So I wouldn't worry too much. But you do need to know stuff like 1's complement, 2's complement. And if you need a reminder, I can go over. Does everyone know 1's complement, 2's complement? Remember how to do that?
The complement, you change 0 to 1 and 1 to 0 and you add something.
Yep. Yeah, give me a sec. I'm going to pull up. Okay, I'll just do a quick example of multiplication in binary first, and then we'll get into the negative representation. Okay. All right.
Same thing.
Wait, are these going to be signed or unsigned?
I'm doing unsigned multiplication. Okay.
Examples are going to be unsigned as well.
Probably. This is probably going to be too big. I'm not going to do this. I realize there's going to be a lot of addition. Okay. So he's covered stuff like different types of multiplication methods in class. Okay. There is the array multiplier, which is what we're going to do. If you were to actually implement this into hardware, it's a very, very inefficient method, but it's still the most understandable to us because it's the exact same multiplication that we do in decimal. Okay, there's obviously this more efficient method for hardware usage, which is called the shift and add multiplier. Because what are you doing when you multiply numbers? Like when you do 3 times 4, what are you actually doing? What is the multiplication operation? Yeah, so you're doing repeated addition, right? You're doing 3 plus 3 plus 3 plus 3. Okay. So when you're actually implementing stuff in hardware, that's the reason why you've seen these other types of multiplication methods, because doing it in that way is more resource efficient than the way that we're going to do it now. But I'll still show you because it's the easiest for us to understand, and we can all do it this method. So quickly, let me think. We can do an example in just normal decimal, and then I'll just go straight to the binary one and show you how similar it is to what you already know. Okay. So let's do. Okay, so in decimal, you guys all remember multiplication? We've forgotten how to multiply? Okay, that's okay. I know that it's been a while, but all right, I'm just going to walk through this example just because I'll show you that you can transfer these skills directly to the binary method. So what do we do first? Well, we multiply in our ones place by the top digit up here. So what do we get? We get 15. So we do 5. We carry the 1. We do 3 times 1 plus 1, which will give us 4. Okay, now we are multiplying by 1, but of course it's in the tens place, so we're multiplying by 10 here. And if you remember from those elementary middle school days, you add this 0 here because you are now multiplying not by 1, but by 10, right? You're adding that 0 there just because you're multiplying 1, 0, right? So 1 times 5 is what? It's 5. Okay, 1 times 1 is 1.
Where's the mouse for that computer?
Yeah, I don't know.
Okay.
Also, the mics don't work. So. All right, so what do we do now? How do I get my final multiplication result? I add them, right?
I think there's some chat messages, but I don't think we can see.
Oh,
them.
the mouse, the cursor for that thing?
Yeah. Yeah, just like get rid of the AI overview and make the participants lower so we can see.
Get out of here. I can't see anything.
Down. Slightly down. Slightly down. Quick. There you go.
All right, what is everyone saying?
He's asking if we want to know for counters yet.
No, we did not go over counters yet, but we can go over that in a second. All right, let's finish our multiplication. All right, remember, what do? We add, right? 5, 4 plus 5, 9, 1. Is that right? I don't know if it's right. I think it's right. Can anyone confirm with me that this is right? Looks good.
That's right.
Okay, so I haven't forgotten how to multiply. Great thing is, just take this exact method and go ahead and do it in binary. All right, but the big thing is we're not multiplying in decimal anymore, so we can't do 5 times 3 get 15. We have to work in binary. So what do we have? We've only got the values 0 and 1 to work with. However, it's very simple. So for this first example, we have to do 1 times 1, which in binary is actually just 1. It's super simple. So, all right, and then we do 1 times 1 again, we get 1. We do 1 times 1 again, we get 1. Great. And then we get 1 times 0, which is 0. All right? Very clear. It's very simple when you're just doing 1-bit binary multiplication, right? 1 times 1 is 1. 1 times anything else, meaning 1 times 0 is going to be 0, and 0 times 0 is 0. Those are the only possible combinations you can have. Great. Now, what's the next step? We've we've multiplied this 1 here by the number on top. What do we do next?
We should add a 0
Mhm.
the right position.
Yep.
Start the multiplication.
Yeah. So here we're not multiplying by the 1's place. We're multiplying by the 2's place. So we have to add this extra 0. Same thing here where we had to add the 0 because we're working in the 10's place. This one's very, very easy because we're multiplying 0 by these numbers, which will give us 0 every time. So we can just do 1, 2, 3, 4 zeros. All right, does that make sense? And then what's next? What do I do? The next one. We're moving up from the 2's place to the 4's place, so I have to add 2 zeros of buffers. Okay, just like you would in normal multiplication. All right, and then we're going to multiply again. And what you'll notice in binary, because it's literally just 1s or 0s, when we're multiplying this 1 by this whole digit, it just stays the same, right? This number up here doesn't change in our result, so we can just write it out as 1, 1, 1, 0. And then for the last one, we have to add 3 zeros of padding, and then we do 1, 1, 1, 0 because it's 1 times that stuff on top. All right, and then what do we do to get our final result? Add. All right, so we get, let's see, we have 1 plus 0 plus 0 plus 0, which is just 1. Hello, Jason. The next column, we have 1 plus 0 plus 0 plus 0, again 1. And then we have 1 plus 0 plus 1 plus 0. What do we get?
0 with a carry.
Right. So we get 0 with a carry because the result is 1, 0, or 2. So that's why that 1 goes to the next spot. So what is the next result? It's 1 plus 0 plus 0 plus 1 plus 1. It's
1.
Right, 1 with the carry. And then what do we get here? Yep. And then what do we get? 0 with 1 carry. There you go. So can anyone explain to me, just by inspection of what I did here, why would this take up a lot of hardware space?
You need to use multiple adders.
I mean, that's true, but what about this? I mean, this step, you have to have this value, this value, this value, and this value all at once, right? So where are you storing that? Yeah, probably in registers, right? So, I mean, you at least need a few registers to store this stuff. But of course, there's more efficient methods that allow you to use just 1 or 2 for way bigger numbers. Because think about it. If we did that big question that I had set out before with 10 digits, think about how many registers you'll need to store all those values.
A lot of
Right.
registers.
I mean, it's a very, very expensive method. This is a very simple method, but it's very expensive. Okay, so that's what I would,
There are no other methods?
Huh?
There are no other methods?
yeah, so in class, he's been talking about the shift and add algorithm, and we've also got a video about it online. Okay, but that's going to be a more hardware efficient method where you're not using as many registers. And that's the main reason why he did it. If any of you guys have taken computer organization, that is like the method that she covered, Dr. Resch. I don't think she's teaching it anymore. But she covered that one. It's called the shift and add, where you're just using 1 or 2 registers to do an arbitrary sized multiplication.
I think she still has one section.
So she definitely did it. I was in the class last semester.
Yeah,
Oh, yeah?
I think Dr. Rush still has one section that she's teaching, and then the other guy has one as well.
Okay. Yeah, I didn't know, but I do remember from the class that
Yes, question?
You said you had like a video.
Yes, it's on the EEL3701C Digital Logic YouTube channel.
what is it?
How many bits for multiplication question?
Most of the topics are covered.
How many
yeah.
bits? Okay, so how many bits do you?
So, kinda crazy.
How many bits is it here? We've got 7 bits, right, as our final result. What's the biggest possible result we can get by multiplying these 2 numbers together? 8. 8 bits. And how did you get that?
Yeah, no, you have to do the multiplication.
Yeah, so if you look at the 2 digits here that you're multiplying, you at least need, I mean, given they're the same size, you at least need 2 times the width of this number, the multiplier, right? So you at least would need, at the worst case, at least 8 flip-flops to store the result of this multiplication. Here, we're lucky. We only need 7, right? But
Would we have to put a leading zero?
no. Just like you wouldn't write a leading 0 in decimal, you don't need to write a leading 0 here. However, in a hardware implementation, of course, those leading zeros, they still exist. Like the hardware, you still have this extra flip-flop. You'll still have an extra flip-flop that's storing a value. It'll just be read as 0, right? Because, I mean, you don't change the amount of flip-flops you have based on how many digits are in the result, right? If your result has 7 bits, then you're just going to use 7 of them, and that last one is going to be a 0. Does that make sense? Okay, are there any questions about binary multiplication? You can do this in other bases too. I made a video about it and I posted it with base 5, base 2, base 4, I think. So
Where's base 3?
I didn't want to do base 3, but you can do it in any base. Maybe we'll give you a hexadecimal multiplication question. Or base 37, like Dr. Schwartz would do, right? Did he ever do that?
No, we didn't have base 37 multiplication on the exam, but we did have a base 37 addition question on the exam.
You use
Like-
the alphabet for.
He literally did like the numbers 0 through 9, then the entire alphabet, then like a question mark, hashtag, ampersand, exclamation mark, period.
Yeah.
So
So
there was a Greek letter in there too, I think, just all the way to make it to 37 different characters.
and think about it. I mean, listen, binary is easy for us to understand, but when you're using computers, usually you'll see stuff written in hex, or even worse, you'll see it written in base 64. I don't know if you've ever seen that, but base 64 is a common compression thing where you take this bigger thing and you shorten it by using symbols, just like you do in hex, A, B, C, D, etc. But use all the capital letters, all the lowercase letters, all the symbols, right? And you're using them to encode it into a smaller thing, right? That's why we like to use hex. How would I write this value here in hexadecimal?
You just see.
Yes, that is correct. Whoever said 5 Ds, that's right.
Why? Can you explain your very quick methodology?
I just finished lab 4, so I was looking at them.
Okay, that's good.
So I just saw 0, 1, 0, 1, that's
Right.
5, and then 1, 0, 1, 1 is 11. So I know A starts at 10, and then B 11, C 12, and so
Right.
on.
So we're going from base 2 to base 16. What do you see when you go from base 2 to base 16? What is 16? It's 2 to the 4.
Get 4 beats.
Okay, great. Exactly. And so you can basically group the number into 4-bit things here, and then you just look at what the value is in each of these groupings. So 1, 0, 1, 1, 11, right? That's representative of B. And then the first one is 0, 1, 0, 1, because you're adding that leading 0. Doesn't affect the value, but it's there. we get 5. So
I was gonna say the most common unit of storage you'll see in low-level hardware at least is bytes. Everything revolves around bytes. Bytes are groups of 8 bits, right? So, and you'll most often see bytes as 2 hexadecimal digits. Bytes are very important. There's a lot of stuff about like byte aligned. Then 2 bytes is a word, and there's some other nonsense there too. But you'll learn that later on.
Trying to base 4.
is base 64 like Minecraft items? No. I would not say it's like Minecraft items, but anyways. All right, the reason why they use 64 in Minecraft is because the data types are in powers of 2. Okay, so they're using a variable that's 2 to the power of whatever, and that's how it works. Okay, so anyways, how on that same note you were able to convert from binary to hex very, very easily? What if I asked you to convert to base 8?
I'll look for the
3.
Yeah,
Yes, 3 digits. Octal.
So again, 2 to 8 or 2 to the power of 3. That's how we know we can actually use that trick, right, of grouping it into groups of 3.
Top question. Can
Right.
I do like base 4 and do 2?
Base 4, you say?
I mean, yeah, if you wanted to do in base 4, which you would never do that ever.
I mean, you could.
Even octal gets used like 0% of the time.
Okay, so remember, like the different prefixes that you'll see on numbers, right? Is for binary you'll see 0B, and then you'll see like a number like this that represents binary. Okay, hexadecimal you'll see pretty commonly with the X, where it's like, I don't know, something like this. You can even use an octal symbol, which I think is what?
It's 0 and then an O. But in some programming languages, it's just a leading 0, which is very weird.
Yeah, so it'll look like this, or it'll look like just this, and it'll be like, I don't know.
Yeah, it's odd. In some more niche scenarios, you may see a B or an H after the number to represent binary or hexadecimal. But that's kind of not as important.
Yeah, so again, if you see something like that and we don't specify what it is, make sure that you know the prefixes. Okay, hexadecimal is the most common one you'll see, especially if you take microprocessors. You'll never get it out of your brain. Okay, you'll see 0x because that's how it's stored and read on the computer, right? A lot of times, as you said, stuff is stored in 8 bits or 2 hex digits. So we really like to do it like that. All right, are there any questions about those number systems?
Can you give an example on like negative numbers? Those throw me off a lot.
Okay. What are the different types of negative number representation?
Yeah, look at that. You're at 37 pages. It's like 3701.
I'm not going to comment. Okay.
No, we're not doing that.
Ted. You have a question? Uh-huh.
We will probably never give you octal ever, but if we
It will specify.
It'll probably be 0 and then a lowercase o. But I don't think we will ever.
It's more likely to specify base 8 than, using those prefixes. But I swear that they taught me this in some class. I can't remember which one, but probably Comp Org. And they were like, yes, this is important. And it was on the exam. So, okay, whatever. Or it was on at least one of the quizzes that we did. So you never know. You should always be prepared for anything. I don't know what the base.
Into the exam that I can add octal onto it.
Yeah, that's a good idea. I think we're gonna put octal on the exam.
Thanks.
Okay. It'll be base 64 to base 8. There you go. Okay. Who remembers the different multiplication the different negative number representations?
One's complicated.
Yeah. Okay. So what's the difference?
You forgot one. Signed magnitude.
Yeah. Okay. Signed magnitude. That's also one. But the main ones that we would definitely use in our case, and there are different representations that you'll learn, like EEE3701 floating point numbers. Those ones will use signed magnitude representation.
You might. I forgot if you do it.
I swear that in Comp Org you have to learn EEE3701 floating point representation. Yeah. And I'm pretty sure that that's like part of the exam is you have to like convert, right? You have to represent it, and then they just Yeah.
Conform and D-log go very hand in hand if you take
Okay.
them in the same semester.
Magnitude is only for the X. So long. Sign bit, magnitude. And then
Oh.
mantis.
Maybe I don't remember.
Yeah, it's sign bit mantissa then exponent.
I'm pretty sure that there's a single bit. Okay, it doesn't matter, but I'm pretty sure.
Exponent and then exponent. No, you're right. Yeah.
Everyone has.
Okay, all right. Okay.
I took it last so the border is still fresh.
Here, let's see.
Can you give the list again? We got two complements, sign magnitude and one.
One's complement.
Okay. So do you guys remember this stuff? All right. Give me a sec. I'll log into my account. I had some examples of this. Luckily, we won't ask you stuff like multiplying with the negative numbers because honestly, it's not really that important right now. It might come up in the later exam. Of course, there's only 2 exams, so like, a lot of the more complex stuff that builds off of what we've learned here might be on the exam, the second one. But of course, that one will be more focused on the processor design, CPU.
We're not telling them about the secret third exam yet.
Oh yeah, should have
Never mind, disregard that.
should have seen last year. We had like 4 exams last year. Okay. So let's do 2's complement. That one's the most common one, right?
We're going to have to build up to it.
Okay, you want me to build up to it? Okay, let's start with a number in binary. It's a very unique number, right? Okay, how do I do 1's complement to get this in a negative? I don't like sign magnitude. I never used it.
It's
Okay,
the ones go
so what do I get?
0, 1, 0, 1, 0, 1.
Like the leading one, dude, come on.
Oh, I need to add that. Hold on.
Yeah.
There you go.
For a 1's complement number, when there's a 1 at the beginning of it, that indicates that it's negative. Signed magnitude is literally just adding a 1 in front of the number if it's negative and a 0 if it's positive. For 1's complement, you add a leading 0 to your number and then flip the digits, and that turns it negative.
All right. So that's the first method that I like. I hate sign magnitude, so I'm not going to go over that first. But let's do 2's complement. So I'm going to give you a number to represent in 2's complement. I want you to try it first and then tell me.
Why do you say 0 is positive and 1's non-negative?
Those are parentheses.
No, yeah. I'm just saying because 1 just means is negative, 0 means not negative, right? That's why I'm saying it like that. Because it's basically a true or false. Is it negative or not? All right. Let's see. I want you to do this in 2's complement.
Explain what it is first.
No, I want people to try and then see how good you guys are at this. How many bits do I need to represent 27?
They done over any VHDL?
No.
4? Okay.
5?
Okay.
27 decimal.
Yeah, it's negative 27. Okay. So I'll walk you guys through this one. So in 2's complement, if you use unsigned representation of numbers and you have, let's say, 5 bits to store your value. So let's say you have, 1, 2, 3, 4, 5. The lowest value, what's the lowest value you could store in unsigned representation?
Lowest?
Yeah.
0.
Yeah, so you can store a 0. And what's the, in 0 and decimal, what's the highest value you could store unsigned?
1.
Yeah, all ones, which is what?
32.
31.
31.
All right, but it's 32 different values. Okay, so what's the problem with this unsigned representation? I mean, obviously we can't store it in a negative format, right? we can't store these in a negative way, but what we want to do is let's write out a number line here where this is 0. Right now, all we can do is store up to 31. We want to encapsulate negative 27 in there. So one thing that we could do is we could take our midpoint between 31 and 0 and say, okay, this is now 0, and this is going to be 31, and then this is going to be negative 16, I think, right? Okay, so what's the issue here now? What do you mean I'm missing one?
I mean, you don't want 31, you want 32.
No, I'm just asking if I want to store negative 27 as a negative number, does this range actually work for us?
No.
So what do I need to do?
Add another bit.
So we need an extra bit to store this value because our range, when we shifted the range such that our 0 is our midpoint between, right here, we are still able to store up to oh wait, no, it's not 31. It's 15, right? No. We can store from 15 to negative 16, right? But of course we need an extra bit so that we can widen that scope that we can store stuff. And if we add an extra bit, what are we going to get? We're going to get a range that is, let me get rid of this stuff. We're going to get a range that's twice as big, right? Because we're adding one extra bit, which gives us twice the amount of storage space. So we'll be able to go from negative 32 to 31. So how many bits now are we using? Yeah, we're using 6 bits. So that's going to be the amount of bits that we're going to use in our final result. Okay. So now that we know how many bits our result is going to be, we can now do our conversion. All right, I made this mistake on one of the attendance quizzes, I remember. So we start with negative 27, and then we need to express it in 6-bit normal decimal representation, or basically in the positive form, okay? And what's 27 in normal binary? So 1, 1, 0, 1, 1, and then we add a leading 0, okay? Because we need it to be in 6-bit representation, right? So that's step 1. What's the next step?
Turn it to 1's complement.
Okay, 1's complement, which is?
1, 0, 0.
Yeah, so we flip it, so 1's. So I'll just write this as positive 27 starts there, and then we do 1's. Okay, and then what's next? Yeah, so we add 1. All right, so this is our final result. And that's how we represent negative 27. We just have to make sure that we're looking in the right scale, right? So, make sense? Yeah.
Is this sign magnitude, or is this just 1 to 2's complement?
Well, this is just 2's complement, the specific method, right? And that's why I was saying, let's first define the range that we can store stuff, and then let's convert it. And that's how many bits you need to store that number in 2's complement.
You basically never see signed magnitude out in the wild, and you also basically never see 1's complement out in the wild. All like 2's complement is basically the only one really used because you don't have to do any modifications when you want to like add numbers. For instance, like to subtract a binary number, if you add the 2's complement version, that gives you the correct answer. Versus like 1's complement or signed magnitude, you have to do extra work.
Yeah,
Do you see sign magnitude on our exam?
No, it's just not worth it.
You could always see anything. You never know.
You might see signed
No,
magnitude.
listen, it's unlikely, but you never know.
Every question on the final will be
Okay.
a signed magnitude.
But
question.
in any case, here, this is what you would do. I mean, if you want to represent 4 in binary, you just represent it like this: 1, 0. Let's say that we're doing 4-bit signed magnitude representation. Is that 4? 0? No, that's 4, right? Yeah. Okay. And then what we do is we add this extra bit at the front, and that says not negative. Okay. So how do I represent negative 4? I just say is negative, and then I say 4. Okay. that clear? Yeah.
Couldn't you just have 4 with 3 bits and then that left or 0 under the magnitude be the size?
Yeah, sure. You could. I mean, I'm just defining the amount of bits that I'm using. But like, let's say you had 7, negative and positive 7, right? Well, no, 8. Let's say that you had the number 8.
Oh, yeah, okay.
Okay. I'm just defining it. But in a question, you'd probably see like, oh, we're using this amount of bits for our representation. Usually in a computer, it's standardized, like it'll be 8 bits or nowadays 64 bits in a computer, right? But we're just throwing out these random numbers for you so that we understand it, that you understand it conceptually, right? No question?
Yeah, so 10100 is negative or using 4 bit or 5 bit.
For sign magnitude? Is this one that you're talking about?
Yeah, that one.
Yeah, so it's 4-bit representation, but there's an extra there's like an extra 1 flip-flop that stores the sign bit, which is not part of the number itself, but it tells you what whether it's positive or negative. But this also gives you 2 representations of 0, right? Why does it give me 2 representations of 0? Yeah, so you get positive 0, you can have 0, positive 0, or you can have negative 0. All right. I swear this was an exam question on Comp Org, so I'll never forget. Okay. I know it was. And there's also there's a representation for infinity too. I can't remember what it is, right? But
isn't 100 negative 4?
What do you mean?
1,
So I'm not understanding your question.
0,
1100?
negative 4.
Well, if I'm saying that I have 4 bits for the actual value and 1 bit here, which is separate.
No, like if I'm doing 3 bit.
Oh, if you're doing 3-bit, then yeah, whatever the highest bit that you see, if it's 0, it's positive. If it's 1, it's negative. Yeah. You have a question?
So unless you have some other thing to go over, could we quickly do number 6 on the
Okay. Yeah, sure. Number 6. All right.
Number 7 is just the loudest question.
Yeah. So number 7 is the 3-bit counter, I think, right? And I don't know if you really want us to go over that or if you want to do it yourself. That's the stuff that you're doing like right now, or maybe the one that you just did, right? You want us to go over question 6?
Yeah.
Okay.
It's quick.
Yeah. 6A. What is an SR latch?
I don't know. Can you explain it, Mr. Newman?
I'm not even sure what kind of answer you want, but I would say, what's an SR latch? What does the SR stand for?
Set, reset.
Okay. So what do you think it does?
It sets something, it resets it too.
Okay. That's pretty good. Okay. So we have SR, set, reset. Okay. We have an LED or whatever output. Okay. Doesn't matter. I'm just going to draw it like a box. I don't want to draw out the gates. Okay. So if I press the set button, which output becomes 1? Okay. So if, okay, this one becomes 1. Great. If from that spot, so if I have already set, if I've turned on the set, that means that our value of the latch itself, it's holding the value 1, even if I take away the set signal. So if I turn off the set, it'll still hold the value 1, right? Because it's a latch. So if you hear the word latch, just say it stores a value.
What happens when Q is 1? You put set to 0 and then you put set back to 1. What happens?
What?
All right, say that again.
Okay, let's say Q is equal to 1, right? The latch holds the value 1, and then set, you bring it down to 0, and then you bring it back up to 1. What happens to Q?
It stays 1.
It stays 1, exactly. No matter how much you change set, Q will stay 1.
Yeah, so look, all you have to know is once you've set it, you can not erase it unless you reset it. It will not change no matter what you do till you press the on. Right? It'll hold its value. And that's really the benefit of a latch, right? That's our first fundamental block of memory.
And that's why it's asynchronous.
What is that? Oh, asynchronous? Yeah, so it's asynchronous because there's no clock signal telling it, oh, you can only change when I tell you to, when the clock signal comes in. If there's no clock coming in,
once that it changes, it stays like that until you press the reset.
yeah, and there's nothing enabling it. Like, why does the JK flip-flop kind of fix the behavior of the SR latch? I mean, I guess, yeah.
In the SR latch, it's invalid at 1-1, but the JK flip flop at 1-1 will just toggle the value.
Yeah.
Yes.
Yes, and because the clock is being used as an enable, okay? And what happens when the SR latch is set to that invalid state? Do you know?
Your computer explodes.
Okay, it doesn't explode.
Just oscillate.
It'll oscillate, or one could, you know, Q could be set, Q naught could be set. It doesn't. We don't know. All right, that there's a whole the whole reason why we want these more advanced latches and flip flops is because they don't have the ability to be broken like that. If you are designing a computer, do you want your electronics to behave in that weird way? Of course not. You always want to know. What? Oh yeah.
Hell yes.
You always want to have determinism in your designs, because if you cannot predict what your design is going to do, how can you ever trust it? And this is one of the most fundamental things about digital design is you need to be able to be sure that your circuit works the way it does before you go and build something, right? You don't want it to explode. I mean, imagine buying a computer and it just, you know, maybe it could go into an invalid state and blue screen. I mean, it does obviously, but that might not be from their circuit design. It could be just physical, right? But you don't want stuff to be unpredictable. You want it to be working all the time. All right. Any other
Never used that?
SR latches? I mean, I don't know.
Well, SR latches are kind of the building blocks of it. You know, you have an SR latch, then you make an enabled SR latch.
Right.
Then you connect two enabled SR latches together with a NOT on one of the enables, and now you have an SR flip flop. You add a little bit of circuitry to the S and R inputs, and now you have a JK flip flop. I mean, generally, nowadays, I'm not sure how the memory is done. I mean, like, memory in your RAM or in your hard drive or whatever are not done with flip flops because that takes too many transistors.
It's too
and it's
expensive.
very expensive.
Registers on your computer, which there are registers, maybe 64 bits nowadays, but those are extremely expensive because you actually look at how many gates are being used for each one of those. It's actually a lot. And if you need to store, because each one of those things only stores 1 bit, okay? And if you have a 1 terabyte memory, do you think that you could implement that with all of those gates? You really can't. It's way too expensive. Okay, so you'll only really see those flip flops like inside of like the core processor or the CPU. And so you guys doing Lab 4, there are registers in the in the CPU that you're designing. Yeah, it's you're combining registers with the ALU. That's the only place really you'll see registers in the actual computers because they're very expensive, but they're fast, right?
Yeah, caches, RAM, long-term storage, they're all done with different techniques. Registers are only used like very close to the CPU, as Neiman said.
Yeah.
What do we need to know about registers for the example?
Well, I mean, what is a register? A register is just a collection of flip-flops. And what does a flip-flop do? Stores a piece of memory. So what does a register do? Stores a bigger group of memory, right? Usually in a computer, you are not just transmitting 1 bit at a time, right? How many bits does how much data does a modern computer usually transmit at the same time? Usually 64 bits. And I'm sure that you hear the term 64-bit computers, right? That's what it's talking about is how much data is in a register usually, because that's how much data is inside of like one packet, right?
Here we're working with 4 bits.
So in your
Yes.
in your lab, yes, it's only a 4-bit computer that you're going to be building.
It's very small.
And if you take microprocessors, you'll use a computer that works with 8-bit numbers, I think.
Yeah.
But of course, once you start getting into like these processors, 32 bits, which is something that you'll do in digital design, maybe, it starts to get really hard to understand. That's why we're doing like this very small one.
That's step by step.
Yeah, so you got to build up. Again, if you need to go, you guys are free to go, but we'll continue talking about stuff. If you want us to go over counters, we'll be here. Yeah, we can go over that. But if you have to go, I understand. We'll keep talking. I'll keep recording so you can watch it. Yeah.
We just 60 and 60.
Oh, 60 and 60.
Yeah, so when this one is set to 0, the flip flop will have a value of 1. So this one is set equal to 0, the flip flop will have a value
Just to
of 0.
explain what it does, okay? And
Yes. so
explain the
this
behavior. So
one
like,
will
what
set
does the
flip
set
flop
signal do?
to
What does the
1.
reset signal do? That, just explain everything that you know about it. Okay?
Make sense?
DRN.
Yeah.
Yeah.
Pop up
Yeah.
there. No,
Oh, yeah.
I'm saying, do you want to just
Yeah, VCC is one, but I mean like when this.
Sorry,
goes to
guys, I'm just
zero,
trying to
that's like
fix
an
up the
output
screen
of
here.
one. So it's like
This one?
how clear and sets the value inside the flip-flop to zero, that one sets the value inside the flip-flop to one, but they're both active.
Yeah, I'm gonna go over question 7 in a couple minutes, so if you don't want to leave, I'll be here.
So what's happening is that when you place components, occasionally when you place components, Cordis will try to give them the same name as stuff that's already there. You see at this very
In that class, the makeup is
right there. So some you can see that your Lux is getting and Cordis just does this on.
Well, they have to
In that case,
respond.
you can kind of just click it and then
You have to
name
get
it
a response,
whatever.
but for us, like,
And then
our class takes priority over another class.
Okay.
I guarantee you, like, because our core code is. Okay. Purpose of, oh yeah, there's some up there.
The purpose of the clock signal is to know what time it is.
Yeah, clocks are good for telling the time, you know. Okay. Anyone want to explain in their own words what the clock? Yeah.
Yeah. Clock signal.
You asked the question.
Yeah. Well, I'm trying to check.
Oh, okay.
So
Okay.
this is the best way.
That's true.
So a clock signal allows the sequential circuit to operate one command after another.
I wouldn't say command. Okay.
Right.
Why would I say don't use the word command?
Case. Cordis was complaining about that error, and now we're complaining about another error. You can see right.
I wouldn't say command because it sounds like you're talking about a processor specifically. Okay. My suggestion would be to refer to it in the context of like a latch. Like you could even give an example of why just a normal latch, an asynchronous latch doesn't work, and why a clock signal can allow you to make it better, if you know what I'm saying, and prevent those invalid states from happening.
Instead of coming, the box state to allow your latch to operate. They make it.
Yeah, and so that's the best explanation, because the reason why we have a clock signal is so that every memory component that we use, they all update at the exact same time. Okay. I mean, they all are trying to update at the same time. You're trying to keep them in sync, right? That's why we say synchronous.
It's good that when you're simulating, you should have.
All right.
these as outputs.
So that's all you would really need to say. And then what's the difference between the asynchronous and synchronous component?
Async does not operate on a clock cycle and synchronous does.
Yes.
Perfect.
I mean, so basically combinational logic is typically, if there is no clock signal, then yeah, it's asynchronous. It just happens whenever the signals come in at all times. Yeah. Okay. Really? Yeah, sure. Okay. Create a 3-bit counter that counts in the sequence 4, 7, 1, 2, C, and then back to 4. Okay.
You don't know, that's the course code for digital design, which is a required course of your CPE that does more stuff with VHDL. And if you're EE and don't have to take digital design, it's still a good idea to take it.
Yeah. So I might TA for the class again. So if you have any questions, I'll probably be back. I don't know. We'll see. I got kind of tired of it because we build a 32-bit processor using VHDL, which is cool. Omar took the class last semester, so maybe he could talk more about it. But
that processor was so annoying. It was low-key fire, but it was really annoying.
It's cool once you're done, just like all these labs, but not fun while you do it. I'm certain.
Exactly.
Okay. Anyways, so what are the key things that we need to take away from this question? Okay. First of all, the sequence. Thank you. First of all, the sequence. What else? Okay. Not necessarily that, but what flip-flops we're going to use, first of all. Okay. So in this case, it says, I think, D flip-flops. Yep. So what's a delay flip? What's a D flip-flop? I just said it, but what is a D flip-flop? Yeah. Hold on. Go ahead.
It's a flip-flop and it updates on the rising edge based on whether or not D is 0 or 1.
Okay.
Like if D is 0, it'll hold whatever it has. If D is 1, it'll update to the new value.
How long does it hold its value for?
Clock cycle.
A single clock cycle, right? So it's called a delay flip-flop because it can only hold its value for one cycle.
Well, that's mostly right. A D flip-flop, whatever the value of D is on the rising edge, that's what it'll hold, right? So if D is equal to 0, it's just gonna be the Q is gonna be 0 until the next rising edge. Then on the next rising edge, let's say that D is 1, the output is now gonna be 1.
Right.
Yeah.
So look here, I'll go through it. So, all right. For context, Q is the value that the D flip-flop is currently holding. Q plus is the value that we want it. No, I like to do it like this. I don't care.
That's weird.
Okay, I do it like this, but whatever. You can do it. You can put D over here. I don't know. I do it like this.
Q plus is an output, so you should have all the inputs on one side.
No, I do it like this for a specific reason. Okay, because I want to look at every possible combination of transitions that we could have. Okay, and that's the reason why I put them on the same side. I know some other people do it differently. It doesn't really matter. Okay, but I'm looking at every possible transition. So what's one transition we could have? We could have the current value of the flip-flop is being 0, and then the next value is going to be 0, right? So no change. What about if we want to go from 0 to 1? See, you can watch the video later. And then 1 to 1. So this is why I'm ordering it like this. And then we say, okay, what input do we need to pass in to our flip-flop to create these transitions? All right, and I know that this is a little bit different than maybe how he did it on the lab, but for me, this is pretty easy to understand. So to get from 0 to 0 after 1 clock cycle, what do I need to pass in to my D flip-flop? Here, give me a sec. What do I pass in? If it's 0 right now. You pass in 0, right? Next clock cycle, which is Q plus, it just looks at the value at the input and then puts it in, right? So if we want it to be 0 again, well, it needs to read a 0 again. What about if we want to go from 0 to 1? What do we pass into the D flip-flop? All right. What if we want to start at 1? Our current clock cycle, the D flip-flop has 1, and then we want to should be 0, right? Because every clock cycle, it just reads what is coming in through this port and then stores it in, right? It does not hold its value like those other latches and stuff that you have seen. It just looks at the input and then pulls in whatever's there at that time. No, what's coming in is just the data line. Q just represents what the flip-flop is holding at that time. Q plus is what it's going to hold after another clock cycle. Does that make sense?
Wait, so what does he do? How are you writing the output of the, what's your thought process? What does he do? What is the function of it?
Okay, so I'll go through the first two rows so that I can explain why I passed in 0 and 1, right? So if the current value of the D flip-flop is 0, and I'm writing it out here, so it's holding a 0 inside of it. All right, every clock cycle, so if I write out the clock cycles like this, and this is clock, and this is our current state, right? And then this is our data line.
Yes.
So right now, actually, yeah, so currently, the reason why the state is 0, why the memory is holding 0 is because the thing that we're passing in is 0. But what if I want to change it to a 1? Well, what I do is I pass in a value. And at that clock edge right here, it's going, the flip-flop, the behavior of the flip-flop, it literally just looks at the value at D and then says, okay, whatever the value is at D, let's bring it and store it now. Okay, so because this value here changed, this one also changes to 1. Okay.
Yes.
And if I change it back to 1 or back to 0 like this, it will hold its value, okay, until the next clock cycle. That makes sense? So basically, it only reads, and here, I'll highlight this to make it more clear. The D flip-flop's behavior, and just at a high level, it just looks at what is the value of the data line at these specific points, and whatever it is at that specific point, it goes in.
This is slightly nitpicky, but for LabCore at least, you shouldn't, and just in general, you shouldn't change inputs on clock edges. That's bad.
Yeah, so basically what you should do is.
So you can see that in Newman's example, D went up at the same time as clock. So he was changing the input of it on the edge of the clock, but that's not what you want. Like in actual circuits, that is bad.
Yeah, it can lead to some undefined stuff. So this is probably a better example of what you should do when you're doing stuff. All right.
Remember the hold instead of time.
Yeah.
And do we need to know this, like, do you need to know the logic that's inside the flip-flop?
You need to know the behavior.
No, you just need to know like the basic
No.
principle of it.
Just know the
Just need to
behavior.
understand the behavior.
Mhm,
If
yes.
if I understand this graph that you just.
Yes.
drew, I can do the
Yes.
excitation table out of it.
Yes. And this is how I'm deriving that excitation table. And this is why I thought originally, I'm like, okay, we'll give it to you. But then I was like, no, you can actually do it yourself. Okay. So so using that knowledge, whatever I passed in through the data line is what becomes our next state. So what for our third row do we get? We start at 1. What do we pass in to make our D flip-flop turn back to 0? Yep. And then what do we pass in to our G flip-flop to keep it at 1? Right. So again, every flip-flop works differently. They all do the same inherent thing. They have these different behaviors for different applications. In this case, a D flip-flop just says, I don't care what my last value is. I'm just going to look at what it is now, and that's what I'm going to store. Right? But other flip-flops don't do that. So there is a reason why you might want to use different ones for different purposes. But D flip-flops are the most common ones used for registers. And I think that it's covered in class Y. But that's probably the most common one you'll see, most likely because they're very simple to understand. But what about the toggle flip-flop? What does it do? Yeah. Yeah, so if you have something like a toggle flip-flop, you could derive the excitation table by knowing how it works. You just say, oh, whatever comes in, the toggle flip-flop will read that at the clock edge and say, okay, whatever I have inside me now, I'm going to just flip. Right? So it has a different behavior, but it still does the same thing. It still stores a bit. All right? Does that make sense? Yeah.
So the D flip-flop doesn't have like a hold mechanism that the other ones do. Just
Yeah.
constantly read the input.
Exactly. And you can, again, there could be many, many other types of flip-flops. So we could make our own type of flip-flop that has our own behavior and use it. And if we gave you a question like that, you should be able to do it. If we told you how it behaves and what you need to pass in to make it transition from state to state, you could actually make a UF flip-flop, which I think is one of Dr. Schwartz's questions, is he made his own flip-flop with, 3 inputs. And then you had to figure out what inputs do I pass in to create these different transitions. Because every flip-flop, every 1-bit flip-flop has this same transition chart here. Because again, they all do the same thing. It's just what is passed in might be different, right? Because a toggle flip-flop, I'm just doing this for demonstration purposes. But a toggle flip-flop, what would I pass in to get these different transitions into a toggle flip-flop? So I don't want to toggle if I'm going from 0 to 0. So keep it at 0. What if I want to go from 0 to 1? So I do want to toggle. Same thing for the next one. I don't want to toggle here. So look, D and T, they look different because they behave differently, but the transitions are still the same. So if you see something that's like a JK flip-flop, you'll have 2 inputs to your flip-flop, but it still has the same transition. So you'd see something like this. Okay. And we'd probably give you that, but you've seen it inside your lab.
Okay, the T flip-flop is also, like, it also has a clock.
Yeah, they all have clocks. So if it's a flip-flop, it's a clock. And that's why I'm saying they have different behaviors when the clock edge is red, but they all do the same thing.
Can you do like the graph thingy for the T flip-flop?
Yeah, sure. Okay. So again, Q is the value that's being held at that current spot, and then T is our input. Okay. So let's say that it's just initialized to 0. Okay. Our T flip-flop is initialized to 0. If we want it to become 1, what I can do is I can say, okay, I want to toggle now. So will this flip-flop toggle based on my diagram here?
Does it only do it when it's a rising edge?
Yeah, so when? Where should I draw that Q going up?
Only when it's like at the same place.
Yeah, exactly. So I'll do that.
Oh, so it's the same thing, but it's not delayed.
Yeah, but basically what happens is if I were to keep this, so let's say I don't toggle again, what's going to happen?
I was gonna keep at 1.
It's just going to stay at 1 forever, unlike the D flip-flop, right? So that's the big difference. So if we ask you to do it with T flip-flops, you should be able to do it. You just remember they have different behaviors, but they still do the exact same thing. So, and you can derive these tables yourself. Okay. Does that make sense to you guys? Excitation table?
For the D flip flop, like what I have written here is that it reads the input and holds the input until the next clock cycle.
Yeah.
But should I say instead, until the next rising?
Usually clock cycle represents like this whole period. So one clock cycle would be from one rising edge to the next rising edge. There's no difference in terminology.
Okay.
If it makes it easier for you to understand, sure, just say next rising edge.
Okay.
But again, a clock period is just from either one rising to another, or I mean, you could technically define this as a period too, but it's just equal points in the cycle, right? So yeah, you say rising edge if you want, but again, the flip flops could be triggered on a falling edge. They could be, depending on how you implement it. It's not very common, but it's possible. Okay, I doubt that we would give you something like that.
I think
but
lab 2 circular.
Yeah. Lab 2's was like that, but again, it's just to show you that it's possible. But the only thing that matters is that there's a transition, right? In these places where there's no transition, there's nothing for the circuit to react to. Okay, so that's why they don't use those. Like nothing can possibly change in these points where it's flatlined, right?
But Mr. Newman, what happens if you keep T true the entire time?
Yeah, if you keep T true the entire time, it's just going to oscillate, right? Because every rising edge, it's going to flip. So again, that's another showcase of why, even though it does the same thing, just have different behavior. All right. So I challenge you guys to design your own flip flops with crazy behavior. Okay, you could have like 100 inputs to a flip flop. Why would you do that? I don't know. No, but it's a cool challenge. Okay. So what do? We have our sequence. I'll write it again. It says only D flip flops, right? So that's actually pretty easy. But let's first write out our state. So what should we do? Well, we have 3 bits to store all this stuff, right? So we have 3 D flip flops. Can the biggest value in our sequence be stored as 3 bits?
Wait, what is C? Is it C like 1 bit?
No, C's.
So can you store it in 3 bits? No.
But I didn't know that. I just guessed the C.
Well, that's what I'm asking. I'm asking, like, can you store it in 3 bits? No, you can't.
No, you can't.
So what?
Because C is 4.
Right.
Why is C 4 bits?
Because C
Like
is
circles.
equal to 12.
12.
And the highest number that you can represent in 3 bits is 7.
Right. So what's the solution here?
So we use
Okay, well-
4 bits to store the outputs.
Okay.
The next stage.
Yeah. Next state truth table. That sounds promising.
Wait,
The next state, it's only 3 bits as well, right? So you only need to represent.
Well, yeah. I mean, we've only got 3 bits to work with. Like we physically only have 3 pieces of hardware to store things. So we have to find a way to store this in 3 bits.
It's okay. Yeah.
Right?
That's what the question specified, right?
Mhm. Yep.
Yeah, you just name every one of your things. Like for example, 4 could be 001.
Yep.
Or like 000.
Right.
Arbitrary.
Right. So why do we call it state bits? Because we're saying that there's states now. We're not looking at the number themselves. We're just saying, okay, if my first digit is 4, that's going to be state 1 or state 0. Then what's the next one? 7, 1, 2. Oh, shoot, I missed one. C. Okay, and instead of looking at the actual number itself, let's just label these little bubbles here with numbers and call them state 0, state 1, state 2. Okay, so let's say that 4 is our first one. It doesn't have to be because it's a loop. It could be any of them as your starting point. But it does say in the sequence, it says, make sure that the reset starts it at 4. So it's usually easy to just say, well, let's put this one at 0. Okay, what's the next number in our sequence? And again, I could also label this in just some random way, as long as I'm storing them in 3 bits. But I mean, why would I do that? It just makes it a little bit annoying, right? So we usually like to say state 1, 2. Yeah, see it. So let's just label it like that. Yeah. And so why did I physically could not do this with 2 bits. Why is that?
You need 5 states.
Yeah. So 5 states, but only 2 state bits would allow us only 4 different states, right? So the only thing that's limiting your counter design is basically how many states can I hold? How many more states could I have here? Yeah. Yeah, because we've got 5 and we can hold up to 8. So we could actually make our sequence a little bit longer, but we're not going to do that.
You should.
No, I really don't want to do that. You could add EEL too. Okay, let's draw out our table. So let's represent these state bits like this. Two. So we're going to say our current state is represented by these 3 bits, Q2, Q1, and Q0.
Yes.
Okay, and what are the possible combinations of states we can have? Well, we have 0, 1, 2, 3, 4. And again, that's where we actually stop, but I'm just going to write them all out. 5, 6, 7. So these 3 are unused, so there's technically more room to make our thing design bigger, right? You wouldn't add another flip-flop if you wanted more state. Yeah.
So here, don't I need to like repeat every value of the clock, like so if I'm 0?
No. We're saying that these things can only change on the clock edge. That's an assumption that we're going to make. So in our truth table, what I do here. Sure. So what we're going to do in our truth table is we say, the reason why this is called a next state truth table is because it doesn't work the same as combinational logic. We just say, okay, on the next clock cycle, what happens to our flip-flops? Okay, so what happens in this case, we write out Q2 plus, Q1 plus, and Q0 plus. Okay, and these represents what is the next state we're going to. So if we're starting in state 0, which I have mapped to the number 4, what state does it go to next?
7. State.
Right, so state 1. And again, since I labeled them in order, it's very, very easy. It's literally just 1 to 2, 2 to 3, etc. But again, I could have labeled them anything, right? And if I had labeled this one differently, like if I labeled this one 110 for whatever reason, I would put that inside my table, right? And maybe if you were taking Schwartz's class, you'd see that, but you know, whatever. So if I'm in state 1, I go to state 2, right, which is actually represented by number 1, and then to state 3, and then to state 4, and then what do I go to when I'm in state 4? State 0. Okay, and what do I do with the rest of the stuff? Right, so they're unused, so we're just going to say, I don't care what the value is. These transitions can't actually happen, okay, but we can still use them for our logic simplification.
True.
No, it's don't care. Okay, so this just theoretically describes what our counter does, but we don't actually know how to realize this into a physical piece of hardware. So what do we do? Okay. What we do is we say, what flip-flops are we using again? So we have these 3 D flip-flops, right? Because that's what we said at the beginning, right? 3 state bits, 3 flip-flops.
Oh, you're using for all.
Right. Right. So we're using 3D flip-flops. And so what are the outputs of these things? Right. So the output of the flip-flops is the current state. All right, remember this, current state, okay? So it's what the value is now. What are the inputs to the flip-flops? Okay, sure, clock signal, but what else? Yeah, but what are we feeding into this though?
Also, you just save it and then export it again. And then
Yeah, sure.
replace the component in
Based on the maps.
Yeah. So what we're passing in essentially is going to be the next state. Okay. So on the next clock cycle, the D flip-flops are going to give us the next state, right? So if currently we're in state 0, if these are represented as 0, 0, 0, what should come out of this combinational logic? Like what should be outputted from
0, 0, 1.
Right. So we should have the values 0, 0, 1, and they should be sent in to our flip-flops, right? But how do we get the logic from, because we're taking in these inputs, if you remember. How do I draw this? We're using the current state to figure out how to send 0, 0, 1, right? Because we can just, it's really easy to say, yes, we need to send 0, 0, 1, but how do we send 0, 0, 1? Right? That's where that combinational logic is. That's what it's for. Okay. So what do I do? Well, I've got these 3 D flip-flop inputs. So we can say, let's call this one D3, or no, D2. D1, and D0. And these are going to be my inputs of the flip-flops. So I'll write them out here. Okay. So what do I need to pass in to my flip-flops to realize these transitions? And I'll go through the first one. Right. So I'll give you the first example. So for example, what do I pass into the highest bit or the most significant flip-flop here? I look at the current state that it's in. Okay, so the D flip-flop is currently at state 0. I want it to be in the next clock cycle 0 again. What do I pass into the D flip-flop? Yeah, so I pass in 0. Same thing for Q1 and Q1 plus on this one for D1. For Q0 to Q0 plus, what do I pass into the D flip-flop? All right. Okay. So what do you notice with these D flip-flops? Right. So it's always going to be the same. But if you were using a different flip-flop, this would not be the case. And remember, yes, here.
I got it.
But again, what I'm filling it in with is those values from this table, right? And if you really want me to, hit this home again, I'm going to move this over here so you can see that you can just use the table to generate those values. Okay. So here we go. So for the second one, D2 to Q2 to Q2 plus, well, I just go look at the table. Well, I want current Q to be 0 and next Q to be 0. So what do I pass in? I pass 0. Okay. You're able to logic this out because you know the D flip-flop's behavior. But that's why the excitation table is not actually really necessary because you know how it works, right? But you can still use it. So for the next one, 0 to 1, well, I look, 0 to 1. Oh, I pass in a 1. Okay. Makes sense? And so you keep going. And you notice for D flip-flops, it ends up being all the same, and then whatever. Okay, but it might not be. What if we asked you to use one T flip-flop, one D flip-flop, etc.? If, for example, this last column was using a T flip-flop, what would I do? I go to the table with the T flip-flop and say, if I want to transition from 0 to 1 on a T flip-flop, what do I pass in? I pass in a 1 to the toggle flip-flop. If I want to pass in a 1, go from 1 to 0, I pass in a 1. 0 to 1, 1. 1 to 0, 1, etc. So it's different, right? D flip-flop is super easy because it ends up matching the table. But if you weren't using a D flip-flop, which I will heavily warn you, we will probably not ask you to use D flip-flops. We'll probably ask you to use a different one. Okay, so just remember that. And then what do we do? So what do we do now that we've gotten all this? Yeah. Okay. So we have the Q2, Q1, Q0. That's fine. But we have to first generate this combinational logic block. All right. So we have to first make the circuit that takes in the current state, Q2, Q1, Q0, and converts it into the next state. So what do? What are the inputs to this little block here? Right. So the current state. What are the outputs to that block? The next state. Right? And of course, it's the next state, but not just the next state. It's the stuff that goes into the flip-flop, right? So yes, it's the next state, but it's the next state that's encoded for the flip-flop. So it's this stuff. Make sense? So do not get confused about this in the exam. Like, do not make the equations based on these inputs and these outputs, right? It'll never be this input, this output. It'll be these are the inputs, these are the outputs. Okay. And so you can get your equations. You get D2, D1, D0 equals something. All right. And we can do this very, very easily. I don't know if I'll actually solve for it, but I'll just show you the steps. You make your K map like this, and then you fill it in. And if we're trying to solve for, let's say that we're trying to solve for D2, which column do I look at to fill in this table?
Q2.
Well, what column do I look at to fill in the table here? This one, right? Because we're trying to generate the equation for that specific flip-flop's input here. We're trying to generate the equation for this output, right? And you're gonna have to repeat this process each time. So let me just quickly go through it. Okay. So when Q2 0, 0, 0. Okay. So again, remember, I'm only looking at this column. Don't look at anything else. So we have 0, then we have 0, and we have 0, 1, 1, which is 1, 0, 1, 0, which is 0. And again, remember, these are the inputs that I'm looking at. And then for 1, 0, 0, it's 0. And then what do we have for the rest of them? Don't care values. All right, great. So how do I finish this up? Let's do a sum of products term here. Let's circle these two. I think that's the best I can do. And that gives us Q1, Q0, right? Because Q2 changes. So that means that D2 is literally just equal to Q1, Q0. So if we were to actually draw our diagram here, so let's say that this is Q2. This input goes back. And for just this specific one, that's Q2. And then, of course, there's the other inputs coming from the other flip-flops. What's our equation? It's Q1, Q0. So let me draw all the flip-flops here. So I'm not going to draw these big wires across the page. I'll just redraw them coming in from the other side. But again, they are the same. All right, so Q1. All right, so what goes into this specific flip-flop, which is D2? Well, it's just that function that we generated here. So we know that it's Q1, Q0. I'm just writing it there so I remember. So what do? It's Q1 and Q0. So what's our combinational logic going to look like? It's just an AND gate. All right? Repeat the process for the other two flip-flops, and you'll get some other circuit for this input, some other circuit for that one. All right, and that finishes the next state logic. Does that make sense? Do you want me to go through all of it, or do you want me to just skip that part? I mean, it's pretty easy once you know. Okay. But what's the missing step here? If we wanted to display the number, what are we supposed to do? Right. We need 4 bits to display our number, right? So what do? I've already built this combinational block for the next state stuff. We need another combinational block to convert our current state into a 4-bit output, right? Because we need to display stuff like C and stuff. We can't do that with only 3-bit. Yeah. I mean, it'll probably be a component that works like that. But we'll design a custom one. Okay. So we're taking in a 3-bit value. And again, remember, we did this type of state mapping, right? We labeled them 0. Obviously, 4 is not 0. So we need to get something that converts 0 into 4, 1 into 7, 2 into 1, 3 into 2, and 4 into C. We need to make a combinational logic block that does that. Yeah. Yeah. So I'm not going to actually solve all that, but I'm going to write out what are the inputs to our combinational logic block here that converts all that stuff. So 3 inputs again, and then our 4 outputs to the, display, which may be our Y3 to Y0. So what are our inputs here? No, the current state. We always want to only see what we're at right now, right? So our inputs are going to be Q2, Q1, Q0, and what's our outputs for this specific combinational part? Yeah, Y3, Y2, Y1, Y0. Okay, and I'm just going to do a couple examples. I'm not going to fill this all out, all right? But let's say that currently we're in state 0. Based on that, what should we be sending to our 7-segment decoder, for example? Yeah, we should be sending out the binary value of 4, right? So let's do that. So we just send out 4. And if we're doing this sequence, then if I'm in state 1, what do I send out to my thing? I send out 7. And then if I'm in state 2, I send out what? Send out 1. And then if I'm in state 3, I send out 2, right? And then what do I send out in state 5? C, right? Which is 12. So that's 8 plus 4, 0, 0. Okay. Does anything not make sense about this? And again, these are outputs to another component, which is the 7-segment decoder, which again, you designed one. We would not ask you to design that part. Okay, you can just assume that it'll go into the 7-segment decoder. You guys remember that component? 4-bit input, and it spits out the display stuff.
The 7-segment was what we used to display the
Mm-hmm. Yep. So yeah, I'm not telling you to design the actual decoder, but just the inputs to the decoder, right? And that's it. So then finally, you generate more equations. You generate an equation for y3, y2, y1, y0. And these will be logic equations that you can just use logic gates to implement. So maybe you'll have a couple gates in here and they route out here. And then all together, you connect everything together and then you're done.
You think that's like a type of question that's gonna be like one of the more, I guess, complicated in the exam?
It's going to be the last question on the exam.
How long is the exam question?
It's 2 hours. It's going to be, I think, around 12 to 14 questions. Okay. And so, and also just a couple other signals that you need to remember is the clock signal. I'm just going to attach them all together. But again, you don't need to do anything with it. Just make sure that they're labeled. What about the reset? There's those signals called like pre-clear and preset. You guys remember that one? So you would just put it on here. I think
preset is for reset and pre-clear is for set.
Record is PRLN, right?
I don't remember. I don't know what they are.
PRLN and PRLN.
Yes.
Okay. Okay, so just use whatever is on Cordis or whatever. I mean, if it's clear that you're talking about preset and pre-clear, that's fine. I don't care. Okay. So if you remember that, that's fine. So what do you need to do? When the reset happens, we need to make sure that it goes to state 0, right? So if the reset turns to 1, what do we need to set all the flip-flops to? So that it outputs a 4. Yeah, so we need to set all the flip-flops to state 0 because state 0 is the thing that outputs 4. So what signal or which one do I attach the reset to? The pre-clear or the preset of all of them? Yeah, so I want to make sure that once the reset is activated, clear everything. Okay, but what if I wanted to start at 101? What would I do? If I wanted this one to be 1, this one to be 0, and this one to be 1, I would just set this one, clear this one, and set this one when the reset happens, okay? And so you would just label it, you would just label it like reset goes into that one, etc. Like that's how you'll do it. And if you can do that, then you are perfect for the exam. Okay, you will be perfectly fine. Are there any questions about anything that I did? I hope that helps a bit. Practice the same thing, but instead of using like do the exact same question that's right here, but change the flip-flops. Maybe use 3 different ones in the same circuit. See if you can do that, and if you can do that, then you will understand everything.
The only one we need to know is the D, the T, and the J, right?
Mm-hmm. I mean, there could be I think in the lab quiz you had like an SR flip-flop, but again, I don't think that's something we would test because it's kind of a joke flip-flop.
So for lab 3, when we use like the decoder, like we just had to import that. We can design that ourselves. So that one was like specifically designed for a 7-segment. So you take.
Yeah, you remember you did it in lab 2.
Yeah.
You designed it. We just redesigned it and then gave it back to you in VHDL.
Okay.
It's the exact same thing that you built in lab 2. And you would not have to design that again. I mean, that thing is really annoying. All those K-maps, if you remember, we're not going to ask you to do that again.
What was that?
The 7-segment decoder.
Yeah.
Remember, it's just a component. Like it's a component that you pull in. It pulls in a 4-bit value and it sends out an 8-bit signal that goes to the display that looks like this. You remember? Or like this. Right, so that's something that you design in lab 2. if we were to ask you to design a counter with something like this, then that's how you would do it. Again, if you can actually fit all of the things in the sequence in 3 bits, you might not actually have to do this. You could just send it out as you could map 4 to state 4, state 7 to 7, right? You could do that, but only if all those values fit. And I think in the video that I posted on YouTube, that's what I did, right?
How much of the VHDL is going to accept?
It's not going to be much. If you can read VHDL, like if it says something like the output F is equal to A and B, like, or C. I mean, this is just a super easy example, but if you can read this and say, okay, now I need to build a circuit from this. I know what the inputs are. And what is it? This is A, B, C. I can draw the circuit from the statement that I see here, right? And then what do? There's an OR gate. So I do that. And then what's my output? It's F. If you can take that code and convert it into some circuit like this.
Not the other way around.
Yeah, I think that's the most that we will have.
Yeah, but it's not that you could also some diagram like this and we have to put it in the shape.
I doubt it. I mean, I would practice it if you can, but again, it's super easy because all you're doing is just writing out the equations, right?
No, just the sequence.
Yeah, like architecture, behavior, this.
That stuff, no, you will not have to do that. Okay. If there's no other questions, I appreciate you guys for coming. I'll post this video online. If you have any more questions, feel free to message me on Slack or email. And I wish you the best of luck on the exam.